Hello everybody, this is again Mikhail Poisson, and this is our probability lecture number 28. Today we're going to talk about transformations of random variables, how to obtain new random variables out of what we have. So we will apply some functions to that random variables and obtain new random variables, and we will describe that new random variables. That is, we will describe the distribution of that new obtained random variables. So before passing to that part of our lecture, let's just summarize what we have learned up to this point about random variables. So we have studied the general theory of random variables, how to describe that random variables using their CDFs or PDFs or PMFs, for discrete case with PMFs and for continuous case with PDFs. And we have studied some important discrete distributions. Well, we have studied discrete uniform distribution, Bernoulli, binomial, geometric, Poisson, negative binomial, hypergeometric. And from continuous distributions, we have studied uniform, exponential, and normal distributions. But please note that this is a small list of important distributions, namely distributions. So, for example, if you will navigate to some distribution page at Wikipedia, at the end of the page you will find a list of different distributions, and let me just show, say, Poisson distribution. So I'm searching that Poisson distribution. This is, well, I'm not sure why is it. Yeah, this is in English. Okay, this is the page, Wikipedia page for Poisson distribution, and if you will navigate to the end of that page, you will find a list of probability distributions. So this list is divided into some sections. So first you will find univariate distributions, univariate random variables. These are distributions of one random variable, and you'll find some multivariate joint distributions. We will talk about them soon. And univariate distributions are divided into subsections. Discrete univariate with finite support, with infinite support, continuous univariate supported on a bounded interval, etc. Say, we have talked about the Bernoulli random variable, we have talked about the binomial random variable, we have talked about hypergeometric Poisson, etc. And we have talked about the geometric one, and from the continuous, we have talked about, say, a uniform one, from continuous supported on semi-infinite interval. Well, exponential was of this type. Let me find exponential one. Yeah, somewhere here we will have that exponential because it is supported on 0 plus infinity. Yeah, I cannot find that. Yeah, this is exponential distribution, and continuous univariate supported on the whole real line, and our normal distribution is supported on minus infinity to plus infinity. So this is our normal Gaussian random variable. But besides that, you can find a lot of distributions, Pareto distribution, log Cauchy, gamma, etc. So there are a lot of distributions we are not studying in our standard courses. And besides that Wikipedia pages, you can look at this page. I'm suggesting you to take a look at this page. So this is a page for univariate distributions and relationship between them. Say, you can see a lot of distributions here, pictures of a lot of distributions, some block scheme. Say this is normal. If I will hit normal, then that will give some information about that normal distribution. Okay, if I am keeping like this. So it is showing some relationship between normal distribution and other distributions, say, or between binomial and Poisson. Say, let me just check this one. If I am hitting this binomial, so binomial NP, when mu is equal to NP and n is tending to infinity, say binomial is approximated by Poisson. Binomial is tending to Poisson distribution. And if, say, n is equal to 1, then we are getting that Bernoulli distribution. So you will find a lot of this kind of graphs. Say this is standard normal, standard normal. If I will take a general normal and take a change of variable, say x minus mu over sigma, then I will get standard normal. And if I will take mu is equal to 0, sigma is 1 in here, then I will again get standard normal, etc. So you will find a lot of interesting things here. Say there is a zip distribution here. There is our discrete uniform, Poisson, etc. So geometric is here, and a lot more. Say exponential needs to be here, somewhere here. Yeah, exponential with a lot of connections. Yeah, and properties. Okay, so I'm suggesting you to take a look and try to understand the relationship between these distributions. Okay, so let's move back. So let me I want to just name some interesting distributions. Well, one interesting and important distributions, of course. One of the distributions is beta distribution. Beta distribution is continuous distribution with two parameters, alpha and beta. There are non-negative parameters. So x is beta distributed if the PDF of x is given by this formula. So c times x to the power alpha minus 1 times 1 minus x to the power beta minus 1. And this is for the interval 0, 1, and our function is 0 outside. C is some constant such that chosen in that way that integral of f is 1 over the real line, in fact over the interval 0, 1. So C is some constant. Usually we are considering some particular cases of this when beta is 1. So if beta is 1, we are obtaining some constant times x to the some power. And these kind of examples are standard in our text, in our probability course. The next one is gamma distribution. Important distribution is gamma distribution. It has again two positive parameters, alpha and beta, and x is gamma distributed with that parameters if the PDF has this form. So x to some power alpha minus 1, alpha is this parameter, times e to the minus beta times x, if x is positive and 0 otherwise. And c is normalizing constant. So c is chosen in that way that the integral of this function over the real line is 1. So the integral from 0 to plus infinity of this expression needs to be 1. So out of that we are calculating that c. And we can see that if we will take alpha to be equal to 1, if I am taking alpha is 1 here, so I will have x to the power 0, so this is 1, and I am obtaining e to the minus beta times x. And if you will calculate the constant c in that case, you will get that c is beta in that case. So we are obtaining, if alpha is 1, we are obtaining beta times e to the minus beta x. So our exponential, that was our exponential with parameter beta, was just a particular case of gamma where alpha is 1. Alpha is just taken to be 1. So gamma is the generalization of our exponential distribution. So, and you will meet during your stat course several other distributions, say students T distribution, chi-square distribution, two very important distributions for the statistics, and maybe you will learn also about F distribution. Okay, the next important distribution I want to just quickly describe is the Bamford distribution. So one question, do you think that all digits are equal in the sense of rights? Well, I mean, this is the Bamford law or Bamford distribution. So in many numerical data sets, real life data sets, the chance that the first digit of a chosen number, so we are choosing a number from that data set, the chance that the first digit of that will be k, say will be 1 or will be 2, will be 9, is the following. So logarithm with base 10 of 1 plus 1 over k. So x is that Bamford random variable showing the first non-zero digit out of the randomly chosen number from the data set. And the chance that our data set of numbers will start by 1 is, say, I'm plugging 1 here, I'm getting 1 plus 1, so logarithm with base 10 of 2. The chance that the number will start by 2 is this much, etc. By the way, let me just show how many ones I have. Say this is our data set, small data set of numbers, and I have 1 here. Say I have 1 here. So this number starts by 1. This is 1. This is 1. So 1, 2, 3, 4 ones. I have another one is here. So this is starting by 1. So I have 1, 2, 3, 4, 5, 6 numbers starting by the digit 1 in this slide. Okay. So this distribution is called the Bamford distribution. Why is that important? Well, this is the graph of PMF. In this case, I am drawing by bars, by using bars. So the probability that the first digit of the number will be 1 is 0.3, almost 0.3. The probability that it will be 2 is 0.17, etc. Why is this important? Let me just show one example. So testing Bamford's law. So some data sets. Twitter users by followers count. So this is what the red sign is what is calculated by using Bamford's law. So we have this much records in our data set, and we are calculating how many numbers out of that 38 million are starting by 1, and how many are starting the first digit, the leading digit is 2, etc. So we are getting, this is the actual numbers, and that red ones are predicted by, are given by Bamford's distribution, Bamford's law. Or most common iPhone passcodes, well, it has this kind of shape. Or if we will look at the population of Spanish cities, we will have this kind of graph. If we will navigate to, say, Fibonacci numbers, first this much Fibonacci numbers, well, we will have perfect match, etc. So you can test distances in kilometers between European cities, and we are getting this kind of graph, etc. So this much about Bamford's law. You can have a look at these YouTube videos. And by the way, Bamford's law is used to investigate frauds in accounting or elections, etc. And the next important distribution is Zipf law or Zipf's distribution. So it has two parameters, s and n. The random variable x is Zipf distributed, if the PMF probability, the mass function, is given by this. So probability that x is equal to k is c times 1 over k to the s. K is running from 1 to n, and c is that normalizing constant that makes the sum of all these elements to be 1. So it is 1 over the sum of all these kind of numbers. Say if s is equal to 1, if I will take s is equal to 1, n is equal to, say, 4, then I will have probability that x is equal to 1 is some constant. I can calculate that constant. Sure, you can calculate that too. 1 to the power 1. Probability that x is equal to 2 is that constant, the same constant, 1 over 2, etc. So probability that x is equal to 3 is c over 3, and the probability that x is equal to 4 is c over 4. Okay, this is that Zipf's distribution. Zipf's distribution. And why that law is important, just let me show one short video. Sorry. Yeah.
Hey, Vsauce, Michael here. About 6% of everything you say and read and write is the is the most used word in the English language. About 1 out of every 16 words we encounter on a daily basis is the. The top 20 most common English words in order are the of and to. A-in is I, that it for you was with on, as have, but be they. That's a fun fact, a piece of trivia, but it's also more. You see, whether the most commonly used words are ranked across an entire language, or in just one book or article, almost every time a bizarre pattern emerges. The second most used word will appear about half as often as the most used. The third, 1/3 as often. The fourth, 1/4 as often. The fifth, 1/5 as often. The sixth, 1/6 as often, and so on, all the way down. Seriously. For some reason, the amount of times a word is used is just proportional to 1 over its rank. Word frequency and ranking on a log-log graph follow a nice straight line.
By the way, what is that log-log graph? Just let me give a quick thing. So we are talking about this kind of probability. So Pn is some constant over, well, pk maybe. Pk is k to the s. If I will calculate log of this, so log, say, with base e, pk is a logarithm of this. This is the logarithm c minus the logarithm of this, so minus s times logarithm of k. So if I will denote this by x, if I will denote this by y, and say I will denote this by alpha, I will get y is equal to alpha minus s times x. So if x is my logarithm of k, I'm not drawing k versus, I'm not giving this way, k versus pk, but I am giving logarithm of k, that is x, versus logarithm of p. In that case, I am obtaining a linear function, so on log scale. Okay, let's continue. So
a power law. This phenomenon is called Zipf's law. And it doesn't only apply to English. It also applies to other languages like, well, all of them. Even ancient languages we haven't been able to translate yet. And here's the thing, we have no idea why. It's surprising that something as complex as reality should be conveyed by something as creative as language in such a predictable way. How predictable? Well, watch this.
Let's stop at this point, go back. So Zipf's law is used in language modeling and in different places. The next important distribution I just want to mention is the Pareto distribution. Pareto distribution is defined in the following way. So the previous two ones, Bamford and Zipf distribution, were discrete distributions, and Pareto is continuous distribution with two parameters, A and alpha. X has a Pareto distribution with that parameters if the PDF is given in this form. So PDF is C over x to the alpha plus 1 if x is larger or equal than a and 0 otherwise. So this is called also power law. So Pareto law is called also power law. So the sorry. So let me try to draw again. So I want to draw the PDF. The PDF will have the following shapes. This is A. Up to this point we will have 0, and we will have this kind of shape for our Pareto PDF. And C is chosen in that way that the integral of this is 1 over the real line, that is over a to plus infinity. So you choose A, then C will depend on that A. And of course C will depend on that power alpha. Okay. So why that Pareto distribution is important? And maybe you have heard about that Pareto 80-20 principle. So this is leading to this same YouTube video. So let me just switch to that part maybe. Yeah. Yeah, maybe starting from this point.
Word use. It's also found in city populations, solar flare intensities, protein sequences, and more than a century of research has yet to close the case. Moreover, Zipf's law doesn't just mysteriously describe word use. It's also found in city populations, solar flare intensities, protein sequences and immune receptors, the amount of traffic websites get, earthquake magnitudes, the number of times academic papers are cited, last names, the firing patterns of neural networks, ingredients used in cookbooks, the number of phone calls people receive, the diameter of moon craters, the number of people that die in wars, the popularity of opening chess moves, even the rate at which we forget. There are plenty of theories about why language is Ziffy, but no firm conclusions, and this video doesn't contain a definite explanation either. Sorry, I know that's a bummer since we appear to like knowing more than mystery. But that said, we also ask more than we answer. So let's dive into Zipf's ramifications, some related patterns, some possible explanations, and the depth of the mystery itself. Zipf's law was popularized by George Zipf, a linguist at Harvard University. It is a discrete form of the continuous Pareto distribution, from which we get the Pareto Principle. Because so many real-world processes behave this way, the Pareto Principle tells us that, as a rule of thumb, it's worth assuming that 20% of the causes are responsible for 80% of the outcome. Like in language, where the most frequently used 18% of words account for over 80% of word occurrences. In 1896, Vilfredo Pareto showed that approximately 80% of the land in Italy was owned by just 20% of the population. It is said that he later noticed in his garden 20% of his pea pods contained 80% of the peas. He and other researchers looked at other data sets and found that this 80-20 imbalance comes up a lot in the world. The richest 20% of humans have 82.7% of the world's income. In the US, 20% of patients use 80% of healthcare resources. In 2002, Microsoft reported that 80% of the errors and crashes in Windows and Office are caused by 20% of the bugs detected. A common rule of thumb in the business world states that 20% of your customers are responsible for 80% of your profits, and 80% of the complaints you receive will come from 20% of your customers. A book titled The 80-20 Principle even says that in a home or office, 20% of the carpet receives 80% of the wear. Oh, and as Woody Allen famously said, 80% of success is just showing up.
Okay, this much. And there is a comment under this video that 80% of noise in a classroom is because of 20% of students. Okay, so you will meet that Pareto 80-20 principle and Pareto distribution in a lot of real life data. And another video is by psychology lecturer.
And by the time the Soviet Revolution came around, which would be at the latter part of the 1910s, after the First World War, the peasant class had actually established farms, of course, varying productivity. Some of the peasant farmers were very, very good at being farmers and produced a huge proportion of Russia's and the Ukraine's food. Because one of the things, we'll talk about this later as the class progresses, one of the things that you'll find if you look at creative production in any domain, it doesn't matter, artistic domain, food production, novels written, novels sold, money generated, number of companies generated, number of goals scored in hockey, etc. Or number of paintings painted, number of compositions written, anything like that, where the fundamental underlying measure is human productivity, what you find is that a very tiny percentage of people produce almost all the output. It's called a Pareto distribution, P-A-R-E-T-O, and it was studied in detail in scientific productivity by someone named de Sola Price. It's a square root law, so here's the law fundamentally. If you look at the number of people who are in a given domain, who are producing in a given domain, the square root of the people produce half the product. So that means if you have 10 employees, 3 of them do half the work. But if you have 10,000 employees, 100 of them do half the work. Right? It's a very, very vicious statistic. And you won't learn about that in psychology for reasons I have no idea about, because you learn about the normal distribution and not the Pareto distribution. But Pareto distributions govern, for example, the distribution of money, which is why 1% of the people in the general population have the overwhelming amount of money, and 1/10 of that 1% has almost all of that, right? So I think it's like the richest 100 people in the world have as much money as the bottom 2.5 billion. And you think, well, that's a terrible thing, and perhaps it is, but what you have to understand is that that law governs the distribution of creative production across all creative domains, right? It's something like a natural law. And we'll talk about that more, but imagine what happens when you play Monopoly. You've all played Monopoly. What happens when you play Monopoly? One person ends up with all the money, all right? Then you play another game of Monopoly. What happens? One person ends up with all the money. It's actually the inevitable consequence of multiple trades that are conducted randomly. So if you take 1,000 people and you get them to play a trading game, you each give them $100, say, or $10, and they have to trade with another person by flipping a coin. I win the coin toss, you give me $1, you win, I give you $1. If we all play that long enough, one person will end up with all the money and everyone else will end up with 0. So it's a deep...
Okay, can you prove this last statement? Try to think about that. Okay, so let's move back to our lecture. You can watch these videos, you can read about Pareto distribution. I just wanted to show some important and useful distributions more. So this much about that distributions. Let's now talk about transformations of random variables. So how to make new random variables from the old ones and how to find the distribution of that new random variables. So given a random variable, one can form new random variables by applying some functions on x, and we have already used that kind of transforms several times. Say when doing normal random variable standardization. Well, if x is a normal random variable with mean, mu, and variance sigma squared, then the standardized version of standardization is this transform. So we are making new random variable out of that x. And we know that the distribution, we have talked about that the distribution of y will be standard normal. And we have talked about this case too. So if x is uniform in 0, 1, then this transform, if we will multiply by b minus a, then that x by b minus a and add a, then our new random variable y, this transformed random variable, will be uniform in ab. So y will be uniform. Today we're gonna talk about the general version of this. What will happen, what we can say about y if we are applying some function to random variable x. So another example, if x is the price of one Facebook share at the end of the next week, so x is a random variable, and if my portfolio consists of 50 shares of Facebook, then my portfolio price at the end of the next week will be 50 times x. So it will be a random variable. So this is a new random variable out of that random variable x. Now, if x is in US dollars, the closing price of that one Facebook share in 5 days, then if I have a portfolio with 50 Facebook shares and also cash in a deposit account, which is earning at the rate 1% annually with simple interest, then if I made a cash investment 55 days ago with a size $1,000, so I am earning with the rate 1% annually, I have invested 55 days ago, and let y be the price of my portfolio at the end of that 5 days. So I have invested 55 days ago, and I am looking for the price after 5 days. So I will have 60 days, sorry. The price of my portfolio will consist of two parts. The first part is the price of 50 Facebook shares, so 50 times x. This is random. That depends on the price of what will be the price of one Facebook share in 5 days. Closing price of that, and my 1,000 in 60 days will grow to this. So 60 over 365, this is the number of days in years. So I'm calculating how many years will pass. 60 days will be this much years. The yearly rate is 0.01, 1% is 0.01. So I will earn this much money in 5 days. So my portfolio price will be 50x plus this much. So this is a new random variable obtained. This is a new random variable obtained from x. This is a transform of x. Now, the general definition is the following. Say we have a function define it on the real axis, taking real values, and we have a random variable x. The transform or transformation of x is using that g is g of x, and I am denoting that by y. So this is called the transformation of x. Usually it is enough to have, and we will have that case a lot of times, it is enough that g is defined on the range of x. Some examples of transformations say y is equal to x cubed, x is a random variable, y is equal to x cubed is another random variable, 2x minus 1 another random variable, logarithm x or this or that are all random variables. Of course, we need to take care that they are well defined. Say if x is taking negative values, so z will not be well defined. If say x is taking the value minus 1, then this is not well defined. By the way, one point here, if x is taking that value minus 1, if this probability is larger than 0, so there is a positive probability that x is minus 1, then u is not well defined. But if this probability is just 0, well, that's okay. We can define this random variable and consider this random variable. Okay, so say I can apply this function to x. X is a random variable and g is given in this way. So it is t squared if t is less than 3, and it is 1 minus arctangent of t if t is larger or equal than 3. Putting here, plugging x instead of t everywhere, so y is new random variable which takes the values x squared if x is less than 3, the same x, and 1 minus arctangent of x if x is larger or equal than 3. So this is a new random variable obtained from x, and in this lecture we will learn how to find the distribution of that new random variable y. Well, we have talked about this. We need to be sure, we need to take care that our random variables are well defined. Say if x is uniform from -2 to 2, then this is not well defined because x can take values that are negative, values from -2 to 0. So this will not be defined in that case. But if I will write y is equal to square root of, say, x plus 2, well, x can take the value -2, but the probability of this is 0. So this is well defined for us. This is well defined if x is uniform from -2 to 2. Okay. Say if x is Poisson with some parameter, with parameter say 4, then logarithm of x is not well defined because the probability that x is 0 is positive, is non-zero, but I cannot plug 0 here. So y is not defined for every possible value of a non-zero probability value of x. Now, assume x is a random variable and y is g of x. G is given, we know x. The general problem here is to describe the distribution of y, having the distribution of x and having that function g. So this is what we want to accomplish in this lecture. For a warm-up, try to guess the answers of the following questions. And after learning this, after studying this lecture, after learning how to do transformation, you can go back and check if you have guessed correctly. So x is discrete uniform. What can be said about x squared? Will it be discrete or not? And if yes, will it be discrete uniform or not? And the second example is with continuous case. X is uniform from -2 to 2. What can be said about this transformed random variable 3x plus 1? Will it be continuous? Will it be uniform? And if it is uniform, on which interval? And what can be said about x squared? Will it be uniform somewhere or not? Think about this and later check your guesses. Okay. First part is about describing transformations of random variables through the CDF. So describe the CDF of transformed random variable y. Now x is random variable. It can be discrete, continuous, or any general, because we are talking about CDF. This works for any random variable. The CDF of x is f sub x. So because in this lecture we will talk about two random variables x and transformed random variable y, I will write fx for the CDF of x, random variable x, and I will write f of y for the CDF of random variable y. Because we have two random variables, I need to specify for which I am calculating that CDF. Okay, so this is the CDF of x, and y is equal to g of x, transformation of x. And what we want to do, we want to find the CDF of y in terms of the CDF of x and in terms of g, of course. So, not too hard. The general idea is the following. Say fy is the CDF of y. Then by definition, this CDF is the probability that our random variable y is less or equal than x. But we remember that y is g of x. So I'm plugging, instead of this y, the value g of x. So I want to express in terms of x, random variable x. So I will have this form. So y was g of x, I'm plugging and getting this. So what next? At this point we need to solve this in terms of x. So express in terms of x. So express in the form probability. So I'm solving, say, this, and I'm calculating x's in some set. And if I will obtain this, I will be able to calculate, because I know the CDF of random variable x. So this is general idea, but for particular cases I will do some calculations and then I will give some examples. So solving this inequality in terms of x can be not so simple and sometimes impossible. That depends on the form of the g, function g. But let us consider two particular cases when we can solve that easily. So the first case is when g is strictly increasing. So what I want to do, let me first show geometrically. Say this is the graph of our function g. This is the graph of g of small x. And we want to solve g of capital X is less or equal than small x. So what are we doing? Well, we are taking x here. So we want to find all values. Maybe I can write the g of t, not to confuse with that x. So we want to find all values of g that are less or equal than x. So to that end, I'm taking this line passing horizontally through the point x. So this is the line y is equal to x. And g of x is less or equal than x in the case when we have increasing function, so strictly increasing function. In this case, I will have the following. So only this part of the graph is satisfying. So only this part of graph is satisfying. So only these values of g are less or equal than that small x. So that means that my x, capital X random variable, needs to be here. So x is here. So x needs to be here to have that g of x is less or equal than that small x. Well, what is this point? Well, we can find this point easily. If this is x, then this is g minus 1, the inverse function at the point x. So So the solution of this inequality, if g is strictly increasing, will be x is, so I'm solving this, x is less or equal than g minus 1 of x, small x. So I'm erasing this and showing what we have. We have the following, so I'm solving this. G of x is less or equal than small x is equal to x is less or equal than g minus 1, the inverse at x. G is invertible because it is strictly increasing, so g minus 1 is well defined. So if I will go back to the calculation of the CDF of y, that was probability that g of x, that is y, is less or equal than x. So this is equal to that. We are plugging that, and we are getting that probability that x is less or equal than g minus 1x. And this is exactly the value of our CDF at this point. So let me just quickly recall what was that definition of CDF of x. Say at the point A, this is the probability that x is less or equal than A. So if this is our A, this is A, then we are getting, this is the probability that x is less or equal than A. So we are calculating the CDF value at that point. This is A. Okay, so simple. In fact, no need to remember this. I'm always doing the step or doing this calculation step by step every time to obtain the value. Now, the second case is when g is strictly decreasing, and in this case, g is again invertible and g minus 1 is defined, but something will be changed in this case. Let me just give graphically first. So what I have, say this is t, I have this kind of graph. This is g, which is strictly decreasing function. So I am taking x, and I want to solve this. Find all values of x such that g at x is less or equal than x, this small x. So I need to draw this line and find all values here for which the value of g is less than, is under this line. So I will have, this is my point, every, if I will take another color, sorry. Yeah. All values of this interval, all values x from this interval will satisfy this inequality. So I will have, and by the way, this point is this, if this is x, this is g minus 1 of x. So I will have, in this case, x is larger or equal than g minus 1 of x. So if I'm solving this and g is strictly decreasing, then I'm getting x is larger or equal than g minus 1x. So the sign is changed. Just one simple case, say if g is 2 minus x, so g capital X is 2 minus x, and I'm solving this, well, the graph of this function 2 minus t is strictly decreasing, then I will have x is larger or equal, so the sign is changed, and here I will have 2 minus x. So the sign is changed, that is important. Okay, so I will have x is larger or equal than g minus 1x, and if I want to express this in terms of the CDF, well, CDF of x, and then I need to pass two complements. I'm getting 1 minus probability that x is less than this number, less than that number, and this is equal to 1 minus the CDF at that point minus the left-hand side limit. Just recall the following. In the general case, the probability that x is less than a is equal to f of x at a minus. This is the general case. If, of course, x is continuous random variable, then we will have f at a. But this is general case. So I'm writing left-hand limit here. Okay, so we were able to calculate explicitly the CDF of transformed random variable in two cases, if g is strictly increasing or g is strictly decreasing. In the general case stated above, one needs to solve this and then calculate the probability of this to express that CDF of y in terms of CDF of x. So this is one example. Say if we will have this shape of g and we will solve this for any small x. We need to solve this for any small x. Say if x is here, what I will have this kind of things. So I need to find all values of x, capital X, such that g is less or equal than x. G is under that line. So under that line means I need to have this part. So up to this point, maybe from minus infinity to this point. For all values x here, I will have this inequality. Then I will have this range up to this point. Maybe. So if x is here in the red marked set, this set marked by a red color, then we will have this inequality. And then we need to write x is inside that set A. Say A is the union of these two, and then calculate the probability that x is inside that interval A to find the CDF of y. Okay, and A, of course, will depend on that value x. X is here. Okay, so I'm showing what I have. Say this is x. I have the same thing here. If I want to have that g of x is less or equal than x, then I need to have that x is either here or here. So the solution of this will consist of two parts. So x is union of this interval and that interval. If we will have the CDF of x, we can calculate the probability of that event that x is here, and we will calculate the value of fy in that case. Okay. Now two examples, and later we will do a lot of examples about this transformation, about calculating the CDF of y in terms of CDF of x. Now the first one is the following. X is uniform from -1 to 3, and y is 3 minus x. So find the CDF of y and describe the distribution of y. So what I'm doing, I'm writing, I'm not remembering that formula, but I'm starting straightforwardly by calculating the CDF of y. So I need to find the CDF of y. By definition, this is equal to the probability that y is less or equal than that x. Now I am plugging the value of y. My y was 3 minus x, so probability that 3 minus x is less or equal than that small x. Now I'm solving this. I'm solving in terms of x. So probability that x is larger or equal than, I'm taking this to this side, 3 minus x. Okay, because I need to, I want to express this in terms of the CDF of random variable x, I need to pass to complement. So I will have 1 minus the probability that x is less than 3 minus x. Okay, now I need to express this in terms of the CDF of random variable x. And this is, because x is continuous random variable, I can just write 1 minus f of x at this point. So the probability that x is less than a is the CDF value at that a if x is continuous, and x is continuous in this case. So 3 minus x. Now, because I know the distribution of x, I can write the value of this CDF. Well, just recall that, sorry. Okay, I will erase this part. So this was, let me just write that this was f of y at the point x, and erase some part. Yeah, this part. And then write the CDF of x. Now I am writing the CDF of x. So the value of CDF at the point x is, well, for uniform, it is easy to write. So it is 0 if x is less than minus 1. It is x minus a over b minus a in the general case when we have a and b here. So x minus a is minus 1, so I will have x plus 1 over b minus a, so I will have the length is 4, the length of that interval. If x is between minus 1 and 3, minus 1 and 3, and 1 after that, so 1 after 3. So the graph is of this form. The graph of our CDF is of that form. So, yeah. This is minus 1. This is 3. And I will have 0 up to minus 1. Then linear up to 3. And then 1. So this is 1. So this is f of x at the point x, of course. This is the graph of CDF of uniform distribution, uniformly distributed random variable from minus 1 to 3. Now I need to calculate this if I have the value of f of x. So I am doing the following. Let me erase this part and write it here. So f of y at the point x was 1 minus f of x at the point 3 minus x. So this is equal to the following. So 1 minus, well, I love to write in this way. I like writing this way. 1 minus this. So 0. If now I need to plug everywhere instead of that x. So x is here, 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 everywhere. Instead of x, 3 minus x. So I'm writing 0 if 3 minus x is less than minus 1. Here I'm plugging again 3 minus x. I will have 4 minus x. 4 minus x over 4 if here I'm plugging again 3 minus x if minus 1 is less or equal than 3 minus x, and this is less or equal than 3, and 1 if 3 minus x is larger than 3. Now I'm calculating this, so 1 minus 0 in this case. So 1 minus 0 is 1 if I will solve this, x is larger than 4. If x is larger than 4. Here, 1 minus this. So if I will calculate 1 minus that, I will have 4 minus 4 plus x in the numerator. So I will have x over 4 if I'm solving this in terms of x. This part is giving that x is positive, so I'm taking x to this side, 3 to that side. I'm getting x is larger or equal than 0. So 0 is less or equal than x. And if I will solve this, that will give the other side of this inequality. So this is less or equal than 4. And 1 minus 1 if this is true, so 1 minus 1 is 0, if x is less than 0. Okay, so I got this for the CDF of y, and let me draw the graph of that. So we have solved this first problem, find the CDF of y, we have found that. Now I want to graph that function to describe the distribution of y. So this is x, this is f of y here, and I'm taking, say, another color. Well, less for values less than 0, I will have 0. Larger than 4, I will have, say, this is 4. I will have 1. This is 1. And here I will have a linear function which joins that point 0, 0, 2 to the point 4, 1. So I will have linear function here joining these 2 points. So this is the graph of my CDF of y. And clearly this is showing that y is uniform. We have talked about this when talking about uniform distribution. Uniform in the interval, well, this is 0, interval 0, 4. So we have obtained it that our transformed random variable is again uniform, but in other interval. So formally, how to do this, not formally, informally maybe, how to do these calculations. So what we have the following. X is uniform in -1, 3. Then minus x is uniform. So if I have uniformly distributed values in -1, 3, and I will calculate minus of that values, I will have uniform numbers from -3 to 1. And if I am adding 3 to all numbers, that uniformly distributed numbers, I'm just shifting that interval. So this will be uniform in the interval -3 plus 3, so 0, and 1 plus 3, that is 4. So we have, in fact, proved this result when doing that calculations. By the way, please note that this kind of things, this kind of calculations are working when we are dealing with linear transforms. If I will do, if I will do this kind of transform, say z is equal to x squared, then I cannot say this is not correct, that uniform, say, from 1 to 9 or 0 to 9, in fact, the distribution of this will not be uniform, and we will see that. Okay, the next example is the following. So x is exponential with parameter lambda, and y is x squared, so non-linear transform, and in fact this transform is not strictly monotonic, but we will talk about that. It is strictly monotonic, in fact, on the range of x, because x is taking only positive values, so on the positive part this will be strictly increasing. Okay, but without that, let's find the CDF of y without using that strictly increasing on the range of x. So what I want to do, I want to calculate f of y at any point x. So I'm writing the definition of that CDF. This is the definition. Now I'm plugging the value of y, probability that x squared is less or equal than small x. Okay, now I need to solve. I'm just thinking how to solve this in the general case. Well, in the general case, I need to have the following cases. Say, I need to consider all possible values of x, and x can run from minus infinity to plus infinity here. If x will be, say, minus 3, then I'm solving x squared is less or equal than minus 3. No solutions here, so the probability will be 0. So I need to take care that I have solution here. So I'm dividing into two parts. If x is less than 0, then I will not have a solution. So this set will be empty set, and the probability of empty set is 0. So I will have 0 if x is less than 0. And what will happen if x is positive? Well, non-negative. If x is non-negative, I'm solving this, I am obtaining the following. So in that probability, I am obtaining minus square root of small x is less or equal than capital X, and this is less or equal than square root of small x. So if x is non-negative. So x squared is less or equal than x, and x is positive, is solved by this. X is between minus square root of x and plus square root of x. Now I can calculate this. I can calculate because I know how to express this kind of probability. So probability that x is between a and b by using the CDF. This will be, because again we are dealing with continuous random variables, this will be f at b minus f at a. Well, this f is about the CDF of random variable x. So I am using this, let me first erase, and use that for our case. Okay, so in our case, we will have 0 if x is less than 0, and this will give fx at the point square root of x minus fx, the CDF of random variable x, at this point minus square root of x. Okay, if x is non-negative. Okay, so now at this moment I need to write the formula for the CDF and calculate values, plug here, and I will get the CDF of y. So now I'm writing the CDF of our random variable x. So that was given by this formula. Let me write f of x at the point t, say. This is 1 minus e to the minus this rate, lambda times t, if t is larger or equal than 0, and I have 0 if t is less than 0. Okay, this is the value of our exponential CDF, random variable CDF. Now I'm continuing at that point, so I am writing what is the value of this. So the value is 0 if x is less than 0, so this is easy. The other part is again easy. So I need to calculate f of x at the point minus square root of x at some negative point, so this is negative. F at negative value is 0, so this is 0, so this is 0, easy. It remains to calculate the value at this point. I'm just plugging instead of t that value, so I'm getting 1 minus e to the minus lambda times square root of x. If that square root of x is positive, well, I'm getting x is larger or equal than 0. So this is that CDF of y. So we have calculated that CDF of y. Let me just quickly give that method to calculate by using a formula for increasing, strictly increasing, decreasing functions. So if you remember, the calculation was in the following way. If g is strictly increasing, then the CDF of y at the point x was the CDF of x, but calculated at the inverse function of g at x. So if g is strictly increasing. Now our function g is gt is t squared, and we are plugging here x, capital X, to obtain x squared to obtain y. So this function's graph is something like this. So x squared is a parabola. This is g, and it is not invertible. It is not strictly increasing. But important thing is here that the range of x, the possible values of x, if x is exponential, then it can take only positive values. So we will have only this case. So only important part of g is this part. So we can just neglect this. We will have this part, and in this part our g is strictly increasing. If g is strictly increasing, then let's calculate the inverse of g. So inverse of g is calculated in the following way. I'm writing g of x is equal to y. So x squared is equal to y. G of x is x squared. So I'm solving in terms of x. So x is, because I know that x is positive, so I can solve this by having square root of y. Here x and y are non-negative. So x and y are non-negative numbers. So this means that the inverse function g minus y is square root of y for y larger or equal than 0. This is the inverse function. Now I'm using this result. So let me erase this part and calculate that value of the CDF of y. So I am plugging here in the CDF of x the inverse function. This is that inverse function at the point x. So instead of y, I will have x just. So 1 minus, I'm plugging here that value of t. T is this function, so inverse of g. 1 minus e to the minus lambda times t, and instead of t I need to plug this, and this is square root of x, square root of x. If that square root of x is non-negative, and this is the same as to write x is non-negative, and 0 otherwise. So I got the same value here. So you can calculate both in this way and in that way. I'm suggesting, of course, no need to remember this formula, and also this formula works only if g is strictly increasing, but just to solve step by step. Okay, so sorry. Now we have described how to find the distribution of transformed random variable y in terms of CDFs. Now let's talk about what can we do if we know the PMF for a discrete case or PDF in the continuous case. So can we find the PMF of our new transformed random variable if we know the PMF of the original x, random variable x? So I was not giving in that CDF transform examples, the example with discrete random variable CDF, because it is much easier to work with PMF if we are talking about discrete random variables. So what I mean, assume that x is discrete random variable and y is its transform. So we have some function g, we are applying that g to that x, and we are getting new random variable which is y, and we want to describe the distribution of y. First, y will be discrete random variable. Why is that? Okay, thanks. And why is that? And because x is taking only finitely many values, and in that case, g of that values will be finitely many, so y will take only finitely many values, or x is taking only countably infinitely many values. And in that case, either g of x will take countably many infinite values, or it can take also finitely many values. So in both cases, y will take no more than countably infinite values. So y will be discrete random variable. So problem here in this part is the following. Express the PMF probability mass function of y of this in terms of the probability mass function of g. And this is very, very easy. If we have the distribution PMF of x, so x is taking values x1, x2, x3 with probabilities p1, p2, p3, etc. So either this is finite list or infinite, countably infinite. Then the PMF of y will be the following. So I need to write here the values of y, so values of g of x. If x is taking value x1, then the value of y will be g of x1. If x is taking value x2, the value of this will be g of x2, etc. So I will have that the values of y are g of x1, g of x2, g of x3, and the probability that y is taking this value, in which case y will take this value, in the case when x is taking the value x1. So I will have p1, p2, p3, etc. So, well, I'm cheating a little bit, not saying exactly correct thing, but that is when we will get several values of g equal to each other. So what will we do in that case if g of x1 is equal to g of x2? So I'm calculating what is the probability that y is equal to, say, g of x1. Then we will have two cases and we need to unite them. You need to combine them. So I will have what I was saying is the following. Say these values are equal to each other. In that case, I'm not writing the same value two times. So it is not okay if I will write y is taking the value 0 with probability 0.1, 0 with probability 0.2, and say 1 with probability 0.7. This is not okay. So what I'm doing, I'm just erasing this and adding to this. And I'm getting the PMF of y. Okay, so this is that knot I was talking about. So if two values g of xi and g of xj coincide, then we write that value only once and we are adding corresponding probabilities. So in a formal way, in a mathematical way, and the probability that y is equal to small y is we are adding all probabilities such that g of xk is equal to y. So if g at that point xk is giving y, we are adding p of k. Well, much easier to look at some particular examples to solve for examples. So the first example with discrete random variables is the following. So I have the distribution of x. X is taking values 1, 2, 3 with these probabilities, and I am asked to calculate the distribution of x minus 3. So very easy. So I am calculating what are the values of y. So if x is taking value 1, then y is taking the value 1 minus 3. So minus 2. And with which probability y will be minus 2 if x is 1 and the probability of that is 0.2. So what I'm calculating the following. So probability that y is equal to minus 2 is exactly equal to the probability that x is equal to 1. And this probability is 0.2. Okay, so the next value is I'm plugging 2 then y is taking the value -1. So the probability is 0.1. I'm just keeping that probabilities. I'm using that 3, x is 3, so y is 0. What is the probability? The probability is 0.7. So I do not have the same values here to combine, so I'm keeping like this, and this is the answer. The distribution of y is this. It is taking the values -2, -1, 0 with these probabilities. Okay, and the next is find the distribution of logarithm of x. So in that case, for the second, so this is b, y is taking the values logarithm 1, which is 0, so logarithm 1, which is 0, with probability 0.2, logarithm 2 with probability 0.1, and logarithm 3 with probability 0.7. I do not have equal values here, so this is the answer. Let's move forward. So the next problem is we have discrete random variable given by its PMF. So this is the PMF, and the problem is to find the PMF of x squared plus y, plus 2, sorry, for this y. So y, which is x squared plus 2, is taking the following values. So I'm plugging this into the formula for y. I will have 4 plus 2, so 6, with probability 0.1. I'm plugging this, I will get 2, sorry. X is 0, then y is 2, with probability 0.3. I'm plugging 1, I'm getting 3, with probability 0.2. I'm just copying probabilities here. If x is equal to 2, I will have 2 squared, 4 plus 2, 6 again, 0 point with probability 0.4. Well, this is not okay because I have 2 equal 6's, well, 2 equal values here. So I'm just erasing one of them and adding the probability to the other. So 0.5, and I'm erasing just this. So this is the probability, this is the PMF of our random variable y. Very simple. And you can check that this is legitimate PMF, so the sum of these probabilities is 1. Okay. Now with some well-known, name it, discrete distributions. So x is Bernoulli P. So x is taking the values 0 and 1. Failure, success, the probability of success is p. So p, 1 minus p. When I am giving you this, then I am saying that x is this kind of distributed. And the part A is find the distribution of 1 minus x. So 1 minus x will be this distributed. So if x is 0, x can take two values, 0 or 1. If x is 0, this will be 1. What is the probability that this is 1? So I'm copying this 1 minus p. The probability that y is 1 is when x is 0, and the probability of that is 1 minus p. So if x is 1, then y is 0, and probability is p. No equal values here, so nothing to combine. This is the distribution. And we can write for short, this is Bernoulli, with parameter 1 minus p. Because in Bernoulli, this parameter is the probability of 1 of success. Okay, so this is for part A. B, find the distribution of z, which is x squared. So x squared, x is taking values 0, 1, so x squared will take values 0 and 1 with the same probabilities. Very simple, very easy. So nothing to change. So the distribution of z will be Bernoulli, let me write for short, Bernoulli P. And the last one, let me write it here. So maybe I will use another color. So C, part C, V is minus X. V is minus X. So if X is taking values 0 and 1, this will take values 0 and minus 1, and probabilities are copied just. I'm copying that probabilities. Well, the problem, will this random variable, a Bernoulli random variable again? No, because Bernoulli random variable takes two values, 0 and 1, not minus 1. So this is not Bernoulli random variable, just not name it some distribution. This is some distribution. We do not have some name for this distribution. Okay. Now, the next problem is with binomial. So X is binomial with parameters 3, 0.7. So we are doing 3 independent trials. The probability of each, the probability of success in each trial is 0.7, and X is calculating the number of successes in that trials. So X can be either 0, 1, 2, or 3. I can have 0 success, or I can have 1 success, etc. So X is calculating the number of successes in that three trials. So X can be 0, 1, 2, or 3. And probabilities are given by binomial formula. So probability that I will have 0 success means I have only failures. So, well, I can write 0.3 cubed. Well, X is equal to 1 means I have just one success. The probability of that is 3 times 3 to choose the place of that success, which number of trial was success. The probability of success is 0.7, so 1 success and 2 failures. So 0.3, the probability of failure is 0.3 squared. Well, let me erase and write. So squared, 2 is here. X is equal to 2 means that I had 2 successes in 3 trials. To choose that 2 places, I need to write 3 choose 2. 3 choose 2 again is giving 3. So 2 successes, that means I need to have 0.7 squared, probability of success squared. 2 successes independent, so I'm multiplying. And another one was failure, so 1 failure, I'm multiplying by 1 failure probability. And finally, for X being equal to 3, I need to have exactly 3 successes, so 0.7 cubed. So this is the PMF of random variable X. So find the distribution of X minus 1. First part is find the distribution of Y, which is X minus 1. X minus 1. So very easy. Minus 1, 0, 1, 2. So I'm subtracting just 1 from these values. And I'm keeping the same probability. So I will not write everything, but let me just write this, this, and 0.7 cubed here. Well, this is the distribution of X minus 1. We need to have this here and that here. So will it be again binomial? No. Binomial cannot take the value minus 1. So binomial is taking value 0 to some number. So this is not binomial. Okay, so I'm erasing this part. The next one is about 2x. So z, which is 2x. So this is part B. 2x. What is the distribution of 2x? So I'm multiplying this by 2. 0, 2, 4, 6. with probabilities, well, I'm copying that probability, 0.3 cubed, second probability, third probability, and probability that x is 3, which is 0.7 cubed. Well, will it be binomial? No, because a binomial random variable has positive probabilities for 0, 1, 2, 3, 4, 5, 6, if it is for 6. So this is not a binomial random variable because I do not have values from 0 to some number all inclusive. So I have 0 to, for binomial I need to have positive probability of taking the value 1 or positive probability of taking the value 3. So this is not a binomial random variable. Well, just random variable, some random variable given by this PMF. Okay, and finally, the C part of our problem is find the distribution of t, which is this random variable 3 minus x. So 3 minus x, this will give 3 minus 0, 3, 3 minus 1, 2, 3 minus 2, 1, 3 minus 3, 0. And probabilities are, I'm just copying this, 0.3 cubed. This needs to be here, so this goes here, that goes here, and 0.7 cubed here. So this is the distribution of t. And will it be binomial random variable? In fact, yes. It is taking values 0, 1, 2, 3, but this is not enough to have binomial. We need to have also probabilities calculated by using binomial formula. So the probabilities are calculated by binomial formula. And what is that binomial? Let me just write binomial, and you can check that this is correct, binomial, with 3 trials, but here instead of 0.7 I will have 0.3. So you can check that the PMF of this binomial 3 0.3 random variable will be exactly well, this table will give exactly this table if you will write these numbers too. But let me explain why we are getting this binomial random variable. So what x was calculating, so we are doing 3 trials. X is the number of successes in that 3 trials. So if I will calculate 3 minus x, then I am calculating, this t is calculating the number of failures. So this is the number of failures in that 3 trials. But failure probability was 0.3. So t is the failure number of failures in 3 experiments, and failure probability is 0.3. So t will be a binomial with 3, 0.3. So how many trials and the probability of each failure in this case. So we have obtained that by using transform. Okay, so let's move forward. 28.7. X is binomial with parameters n 0.5. So x is binomial with probabilities n 0.5, and y is n minus x. So y is given by n minus x. Show that y is binomial with parameters n and 0.5. So what it means that x is binomial, in this case I will not write with table, but I will write that the probability that x is equal to k. So what x is calculating first, we are doing n independent trials. We have success in each trial. The probability of success is 0.5. X is calculating how many successes we will have in that n trials. So the probability that I will have exactly k successes by that binomial formula is the coefficient binomial n choose k times the success. We need to have k successes and n minus k failures. P is here 0.5. So if I will plug that value of p, so p is 0.5, I will get 0.5, I will get n choose k times 0.5 to the k, another 0.5 to the n minus k, 0.5 to n. So this is the formula for binomial probabilities, binomial case, and k is running, k is the number of successes, it is running from 0 to up to n. Okay, now I'm calculating the probability that y is equal to k. So I want to find y. I know that y is discrete random variable. I need to find the distribution of that random variable. So this is equal to probability. I'm plugging the value of y. Y was n minus x, so n minus x is equal to k. So I'm solving for x. Probability that x is equal to, well, taking this to the other side, n minus k. And I know how to calculate the probabilities with for x, and I just need to plug instead of k, n minus k. So I'm doing that. So this is equal to this quantity, but instead of k, I am plugging n minus k. N choose n minus k times no k here, so I'm just copying that 0.5 to the n, and this is a well-known formula for binomial coefficients that binomial coefficients are symmetric from both sides, so n choose n minus k is equal to n choose k, exactly 0.5 to the n, and this is equal to p, x is equal to k. So for y and x, we have the same PMF. So they are both binomial distributed with the same parameters. So important things, I think here, x and y are both binomially distributed with the same parameters, n and 0.5, but x is not equal to y, y is not equal to x at every point. This is x, y is not coinciding with x, because y is n minus x is not equal to x. Well, this can be equal only if x is n over 2, and that works if n is even, and only if x is that n over 2. Only for one value is x is equal to n minus x. For other values, x can take values from 0 to n. So only for one value can be equal, and that is for the case when n is even. Okay, so we have different random variables which are binomial, which have the same distribution. So in that case, if we have two random variables with the same distribution, we are calling that random variables to be identically distributed. So x and y here are identically distributed. So if x is calculating the number of successes in that n trials, then y is calculating the number of failures in that n trials. But because the success probability is 0.5, then the failure probability is again 0.5. So that's why we have this binomial n 0.5 distribution. So I'm writing that distribution, the definition of identically distributed random variables. So x and y are identically distributed, or x and y are ID for short, if they have the same distribution. In this case, we obtain it that x and y are identically distributed. The next problem is with a geometric distribution. So x is geometric with some parameter p. Will y be geometric or not? So first, let me write the distribution of x, the PMF of x. So geometric is, we have success in one trial. The probability of success is p. We are repeating that experiment independently again and again and again until having the first success. And X is calculating how many trials, how many steps we will do until getting that first success. So I can do 1 trial, I can do 2 trials, I can do 3 trials, etc. So k trials, this is the values of the range of X is countably infinite. And the probability is that the first step will be my success is, that means that the first one was success, and the probability of that is P. X is 2 means I have failure then success. Failure then success, the probability is P times 1 minus P. X is 3 means I'm doing 3 steps, 3 trials to obtain the first success. So that means I have 2 failures. The first 2 trials were failures and 1 success. The last one was success. So 2 failures, 1 minus P squared, 1 success P, and I'm multiplying every probability because we have independent trials. And for K, X is equal to K means the first K minus 1 steps trials were failures and the last one was success. So 1 success and K minus 1 failures. Okay, this is the PMF of our geometric random variable. So part A, what about 2 times X? So the distribution of 2 times X will be 2, 4, 6, etc. 2k. So 2 times X will take all even numbers, natural numbers, and the probabilities will be the same. So P times 1 minus P, etc. So I will not copy. This is going to here. This is the distribution of that. Will it be geometric? No. Geometric need to take values 1, 2, 3, 4, 5 up to infinity. So this is not geometric. Okay. So the next problem is about x squared minus 1. And will it be geometric or not? Let's see. So t, which is x squared minus 1. So I'm plugging this 1. So 1 minus 1 is 0. 2 squared minus 1, so 3. 3 squared minus 1, 8, etc. K squared minus 1, etc. Now probabilities here, P times 1 minus P. I'm just copying. Nothing is changed because I do not have repetitions here. No need to combining probabilities, etc., etc. So the same, this probability goes here. So I have this, and the problem is it geometric or not? Well, of course it is not, because we have 0, 3, 8. We need to have for geometric 1, 2, 3, etc., k, etc. with some probabilities of this form. But we do not have that kind of form for PMF, so this is not geometric. Okay, so I'm not erasing everything, but I'm erasing this part. So the C part is the following. Find the distribution of x minus 1. So Z is x minus 1, which is distributed like this. So 1 minus 1, 0, 2 minus 1, 1, 3 minus 1, 2, etc. K minus 1, etc. This is K. And with probabilities, I'm just keeping that probabilities. P times 1 minus P. This is P times 1 minus P squared, etc. So this goes here. So P times 1 minus P to the K minus 1, etc. So give interpretation for this. Well, will this be geometric? Sorry. Will this be geometric? Well, in our using our definition? No. But if you remember when I was talking about geometric random variables, I was giving that there is another form for geometric. So this is that another form geometric. So x is calculating how many steps we need to do for the first success. And this z, x minus 1, is showing how many failures we have before the first success we had, maybe. How many failures we had before the first success. So 0 failures means the first one was success. 1 failure means that in 2 steps we had success, etc. So this is that other form of geometric distribution. Other definition of that geometric distribution by calculating the number of failures before the first success. And in the general case, so negative binomial was the generalization of that geometric, if you remember. Negative binomial NP was, P is the probability of success in one trial, and N is showing how many successes I want to have. And U is calculating how many steps I need to do to have exactly N successes. So if N is 1, exactly 1 success, that is our geometric. So this is general case, and I'm asking to calculate the distribution of U minus N. U minus N. And the distribution of U minus N, I will not calculate this, you can do this easily. So distribution of U minus N will show the distribution of how many failures we had before having exactly N successes. And this is the other definition of negative binomial which was used in, say, R in the software. So U minus N is that negative binomial distribution defined in R or in some textbooks. So this is showing the number of failures before having N successes. Okay, so let's move forward. X is Poisson. Describe the distribution of 3 minus 2x. Will it be again Poisson or not? Well, so X is Poisson means we will have the following PMF. It is taking values 0, 1, 2, etc., k, etc. And probability that x is equal to 0 is calculated in the following way. E to the minus lambda times lambda to the 0 over 0 factorial, this will give 1. So the probability that x is taking the value 1 is e minus lambda times lambda to the 1 over 1 factorial. E to the minus lambda, lambda squared over 2 factorial, sorry, 2 factorial, etc. E to the minus lambda, lambda to the k over k factorial. So this is lambda to the k, etc. And now I am asked to calculate, 3 minus 2x, the distribution of this. So distribution of this, the values of this will be, I'm plugging 0, 3 minus 0, 3, then I'm plugging 1, 1, I'm plugging 2, I will have minus 1, etc. I will have 3 minus 2k, etc. With probabilities, well, the same probabilities, e to the minus lambda, lambda times e to the minus lambda, etc. So I will not copy everything here. We need to bring to this table these probabilities. Okay, this is the distribution of 3 minus 2x. Is it again Poisson? Of course, no. Poisson random variable needs to take values 0, 1, 2, up to infinity, all values, and not only that all values, but the probabilities need to be of this shape. But I do not have that values starting from 0 to plus infinity. I have just two positive values and all other values are negative. So it is not of this form, so it is not Poisson. It just has that PMF. Okay, so so far about making transform for discrete random variables by using PMF. So that was very easy. You are just plugging, calculating, and taking into account that if you have equal values for the transformed random variable, you are just combining corresponding probabilities. Now let's talk about what will happen if we will have our original random variable continuous and we will do transform with that continuous random variable. So we have already talked about how to find the CDF of transformed random variable having the CDF of original random variable. Now assume that x is continuous, so we are describing our x by using not the CDF, but we are giving with PDF, and usually we are giving our random variables, continuous random variables, through their PDF. And y is g of x, so we are calculating, we are transforming that x, we are obtaining new random variable, and we want to describe the distribution of y. Well, we can have the following cases. The following cases are possible. Well, y can be continuous again, like x, or y can be discrete, and we can have also other cases. Okay, of course we will not talk about this, but let me give examples to show that these two can happen. Say if x is uniform, x is continuous, of course, in that case, and g is this function, cubic function, gt is t cubed. So y will be, I'm plugging x here, so I'm getting x cubed. Then y is continuous, and we can find that PDF of that y. So if x is uniform, g is t cubed, or y is x cubed, then y will be continuous. But if x is uniform in 0, 4, so x is continuous, and the g of t is the integer part of t, then y will be the integer part of x. So y will take the values, say x is taking values from 0 to 4. So integer part of x can be either 0 if our x is between, so let me write that maybe better to write. If x can be between 0 and 1, then y is the integer part of x, will be 0. If x is between 1 and 2, then y, which is integer part of x, integer part of this x, this will be 1. If x is between 2 and 3, then y will be the integer part of x will be 2. If x is between 3 and 4, then y will be 3, the integer part of x will be 3, and x can be 4, of course. Let me add it here, x can be 4, and in that case y will be 4. So in totality, y can take only values 0, 1, 2, 3, 4. So finitely many values, so y is discrete random variable. Of course, the probability of this, so probability that y is 4, which is the same, the probability that x is 4 is 0. Because x is continuous, the probability that x will be 4 is 0. So we can just neglect this. So we have 1, 2, 3, 4 values for y. So y is taking these values, and we can calculate the probability that y is equal to 0. The probability that y is equal to 0 coincides with the probability that x is between 0 and 1. So let me write that part, what I am saying. Later I will solve some problems for you, but because we have already that problem almost solved, we can calculate this probability. So probability that y is 0 is the same as probability that x is between 0 and 1. And because we are dealing with a uniform distribution, this is the case of choosing a point at random from 0, 4, and I'm asking you what is the probability that x will be between 0 and 1. So I'm picking a point from 0, 4 uniformly. What is the probability that it will be between 0 and 1? Well, that will be 1 over 4. The length of this interval over the total length, 1 over 4. So if I will write the distribution of y, so y is taking values 0, 1, 2, 3. So no need to write 4 because the probability of that 4 is 0. And with probability, this is 1 over 4. Okay, so what is the probability that y will take the value 1? This will happen in the case when x is between 1 and 2. And this is again 1 over 4 because the length of this interval is 1 and we are dividing to the length of this interval. 1 over 4, so again 1 over 4, again 1 over 4. You can calculate and obtain this. So in other way I can write this in the following way. So y is discrete uniform with values at 0, 1, 2, 3. So this is the distribution of y. So in this case, y is discrete and the PMF is given by this. Well, PMF is this. Okay, so it can happen that y is continuous if x is continuous. It can happen also although x is continuous but y is discrete. Well, this case doesn't have the general theory, so we will talk about the case when y is continuous, and later I will solve some problems like this for discrete case. So what we want to do, we are considering, I'm writing here first we will consider, but next I am not considering that general theory, I am just giving examples when y is discrete. Okay, first we are considering the case when y is continuous. So our problem is the following. Given the PMF, sorry, not PDF, PMF but PDF, given the PDF of x, small f of x, calculate the PDF of y, f of y, in the case when y is continuous. So we want to obtain the PDF of transformed random variable if we have the PDF of original random variable x. So the scheme is the following. First, we are expressing the CDF of y, this, in terms of the CDF of x. We know how to do that. We have learned how to express CDF of transformed random variable by the CDF of original. And then to calculate the PDF of y, we are just calculating the derivative of that CDF, and that's all. Okay, because we know we have some formula for the case when g was strictly increasing, let me just write what we will obtain in that case, and also for the decreasing case I will write. We have a formula to express CDFs of y, CDF of y in terms of CDF of x in these two cases, so I'm using that to obtain relationship between the PDFs. So g is strictly increasing, y is g of x. We have obtained this formula for a relation between CDF. So f of y is f of x at the inverse of g at x point, at the point x. Then I'm calculating, so what I'm doing here, I'm just calculating the derivative of this, which is equal to the derivative of this. So this will give f of y at the point x. So f of y is the derivative of this. So I'm using composite function derivative rule. So it will give, let me erase and show what that will give. The derivative of the outer function, so f prime at this point, times the inner function derivative. So f prime is giving small f. So f prime of x, small f of x. So CDF, the derivative of the CDF of x is giving PDF of x at this point times this function's derivative. So g minus 1, the inverse function derivative. So this is the formula to calculate to calculate the PDF of y in terms of PDF of x. If g is strictly decreasing, then we have this relationship. F of y was 1 minus f of x at g minus 1 and the left-hand limit. But because we have our x is continuous, then we will have 1 minus g minus 1x. So no need to consider this left-hand limit. Now I'm calculating the derivative of this to obtain PDF. PDF is derivative of this. I'm plugging this. So the derivative of this, the derivative of 1 will be 0. So minus the derivative of this. And again, using that composite function derivation rule, I will have this equality. So the only difference is that we have obtained minus sign here. Now we can combine these two cases when g is strictly increasing or decreasing in the following way. If we are doing this transform by using g, which is either strictly increasing or strictly decreasing differentiable function to be able to calculate the derivative, then the PDF of transformed random variable fy will be the original PDF at the point g minus 1x times the absolute value of this derivative of that inverse function. So this is the general form to obtain the PDF of y in terms of PDF of x. But I'm suggesting not to remember this formula, but to do calculations every time to obtain this formula. So I will solve for you several examples. I will show sometimes by using also this formula what we can achieve, but usually I will solve starting from the beginning without using this formula. Okay, summarizing, if we want to find the PDF of y having the PDF of x and having the function g, we perform the following steps. We express the CDF of y in terms of CDF of x. Then we are calculating the derivative of this CDF of y to obtain the PDF of y. Now examples. So at the beginning of our lecture, I was asking you, will the square of a uniform distribution, well, that was not in the 0, 1, but that was uniform. So the square of a uniform distribution, will it be uniform or not? Let's calculate the PDF of that random variable. So what is asking this problem? So do this step by step by doing all calculations. So I'm solving this from the beginning without remembering any formula, without using any formula. So x is uniform in 0, 1. So I want to obtain, and y is x squared, I want to obtain PDF of this. Okay, so first I'm starting by writing the CDF of y. So every time I'm starting by the CDF of y, I'm starting by definition of that CDF. So y is less or equal than x. Probability that y is less or equal than x. This is the definition of our CDF. Now the value of y is x squared, so I'm plugging that. X squared is less or equal than small x. Now I need to solve this, but I'm remembering to solve this for all values of x. So if x is negative, no solution here, empty set, so probability will be 0. 0 if x is negative. Okay, if x is positive, then I can solve that, and the solution will be the interval from minus x to not minus x, minus square root of x to square root of x. Sorry. If x is non-negative. Okay. Now I want to express this. So let me express this in terms of the CDF of x. So what I'm getting is 0 if x is negative, and this is f of x, the CDF at this point minus the CDF at that point. X is continuous, so I can use that formula. Fx at square root of x minus fx at minus square root of x if x is non-negative. Okay, now I can do in two ways. I can use the formula for f of x to calculate this. Then I will calculate the derivative of that after having that formula in explicit form, or I can first calculate the derivative of this, then plug the values of obtained things. So I need to differentiate this and that. I will have the PDF of uniform, and I will plug that values. Okay, so first thing is to simplify. This is 0. Why is that? Because we have x is uniform in 0, 1. Then the value of CDF at any negative point will be 0. Well, if you remember the graph of our CDF of uniform 0, 1 is something like this. This is 1, this is 1. So the value at negative points will be 0. So this is 0. This is 0. Okay, so I am left with the following. X is less than 0 and fx square root of x if x is non-negative. Okay, so I can calculate the derivative of this, then plug the values. Let me do it in that way, or first plug the value because I know that the CDF value, but I'm preferring to first calculate the derivative of this. So f of y, small f of y, let me just erase and write that again. So the PDF of y at the point x is the derivative of CDF, this differentiated, and this is equal to, because this is equal to that, I need to calculate the derivative of this. So if x is negative, I will get 0 if x is negative, and the derivative of this is if x is positive. So I'm not calculating the derivative at the point 0, but for x is positive. It is okay if I will not have the value of this at finitely many points. So our CDF can be non-differentiable at some point, that's okay. So the derivative of this will be the derivative of f at the point square root of x times the derivative of the inner function. So 1 over 2 times square root of x. This is the derivative of square root of x if x is larger than 0. By the way, please be careful. Let me erase and write it here, that these two things and this thing are different things. So this is, we are plugging into function this and then calculating the derivative. Here we are first calculating the derivative at point t, then plugging that square root of t. So this is equal to this derivative times square root of x derivative. So this is from calculus. Okay, now I'm continuing this and writing 0 if x is less than 0, and the derivative of CDF is just PDF. So PDF of x at the point square root of x times 1 over 2 times square root of x if x is positive. If x is positive. Okay, now I need to write the PDF and then I will be able to calculate this. So I'm erasing that part, maybe this part, no need for this already. Now let me write the formula for PDF for x. So fx at any point t, well, we were writing with x, but that's okay, I will write with t, is equal to 1 over the length of this interval, 1 over 1, which is 1. If, well, let me erase and just write 1 here. So this is equal to 1 if t is between 0 and 1, and 0 otherwise, if t is not in, well, let me write otherwise. Okay, now I can calculate this. So I'm continuing. This is equal to 0 if x is less than 0. The value of our PDF at square root of x. So I need to plug here square root of x. So no t here, so I'm plugging just here and there. So I will get the following. The value of PDF at, I'm writing this part. This part will be 1 times, now this part, 1 over 2 times square root of x. If square root of x is this t, this was the value of our t, we are plugging here square root of x. So square root of x is between 0 and 1 means x is between 0 and 1. So x is between 0 and 1. And if square root of x is not in this interval, so if x is not satisfying this, if x is larger than 1 in fact, then we will have 0 again. So if x is larger than 1. So this is the PDF. Well, I can combine just and write in this way. So 1 over 2 times square root of x if x is between 0 and 1. Well, x cannot be equal to 0 because I will have here, I have x is larger than 0 here. So this will work for any x. Here x is positive only. So I will have x is positive. So let me correct here. So between 0 and 1 and 0 otherwise. So our random variable y is equal to x squared will have this PDF. So let me just graph that PDF. So it will not be uniform. So the distribution of x squared when x is uniform will not be uniform anymore. So it will have this kind of shape. So this is x. I'm drawing the PDF of y. So we will have this kind of thing. So it is starting from plus infinity decreasing up to some value at the point 1. So at 1 the value is 1 over 2, so this is 1 over 2, 1 over 2. And we have 0 here, and we have 0 here. So this is the graph of the PDF of f of y. So we will have, with high probability, values are close to 0. So there is an intuition behind that. If I am taking uniform values between 0 and 1, and I am squaring that values, if you know if x is between 0 and 1, then x squared it will be less than x. So the values are getting more closer to 0 if x is between 0 and 1, not including 1 and 0. So I will have this inequality. So squares are just more condensed dense here. So I will have this kind of PDF for x squared. So 1 over 2 times square root of x. Let's go back. Okay. So we have done this by doing all calculations. So the second part is find the PDF of this by using the PDF transform formula. Well, that PDF transform formula is working for strictly increasing or decreasing transformations. Here our transform is x squared, which is t squared, say, which is non-increasing or decreasing on the real line, but because the values of x are positive, are all from 0 to 1, then in that part, and we are plugging that x into g. So we need to consider only the part of g between 0 and 1. So this is enough for us. So g of t between 0 and 1. This is t squared. And in this case, our function g is strictly increasing. So for strictly increasing case, we can calculate that PDF by using the following formula. If you remember, the formula was the following: fy was f of x at the value g minus 1x times the derivative of g minus 1x derivative. Well, in the case of strictly decreasing, we need to put minus sign here. So let me calculate. If y is equal to g of x, which is say x squared, our function g is x squared here. So x is equal to square root of y. So g minus 1 of y is square root of y. So g minus 1x is square root of x. And this is for, in this case, y is larger or equal than 0. If I will plug x here, so I'm writing in terms of x, I'm getting g minus 1x is square root of x. I can just erase and write that in terms of x. So g minus 1 x is square root of x. Now I have everything to calculate. So the derivative of this will be 1 over 2 square root of x, and f of x, well, let me just plug first square root of x. This is small x, this is capital X for random variable, times square root of x derivative. So this is giving the following. Well, this is either 0 or 1. It is 0 if this value is in 0, 1. So I will have 1 times the derivative of this is 1 over 2 times square root of x. If x is between 0 and 1, So if square root of x is between 0 and 1, so this will give between 0 and 1. And this will give 0 if the argument, if square root of x will be outside of interval 0, 1. So 0 otherwise. So we are getting the same value by using this transform formula. Okay, so check the result in R. So generate 100,000 random numbers from standard uniform. So generate from this distribution, plug here, calculate the value of y, then plot the histogram of relative frequencies, and then add theoretical PDF to that histogram to see that we have obtained it correctly. Okay, so let's move to R and see if we can solve that. This is our R. So what I'm doing, I'm generating uniform numbers. So R unif, random numbers, so 100,000, well, let me just use 1,000 first, then I will change this. I'm not adding any parameters because by default it is generating from uniform 0, 1, standard uniform random numbers. So I'm running, Control Enter. Yeah, I have that x. And now I'm calculating the squares of that. Y is x squared. Very simple. I'm running this. So I have that vector of y. I'm doing histogram. So histogram. Forgot to write. Yeah. Histogram of y. Well, okay, I can run that. This is the histogram. This is histogram frequencies. So how many elements of y are in this interval 0, 0.1? So more than 300 elements are there. About 150 elements are between 0, 1, 0, 2, etc. So let's do that for relative frequency, not the number of elements, but the number of elements over the total number of elements. So if I will add here, I'm adding the frec is equal to false. So if I will run that, I will have the same shape, but in terms of relative frequencies. Okay. Now what I want to do, I want to add the theoretical PDF we have obtained, the graph of that theoretical PDF. The graph was 1 over 2 times square root of x. So I want to draw the graph of that function. So t runs, because I am drawing a graph of a function, I need to take some running variable. So sequence, this is a sequence of points from say 0 to 1, because I have from 0 to 1 my histogram, and by step 0.01, say. For each t, I'm calculating the value of my PDF, and the PDF was 1 over 2 times, let me write in this way, 2 times square root of t. Okay, now I'm plotting that graph. So plot t, z, joined by lines, type is equal to lines, yeah, and with bold line width is say 2, and color is red, say. Okay, if I will run this, that will that will not draw over this. So I am first running this par, new is equal to true, new is equal to true, to keep the old graph, and then I am plotting this. Well, let's see what happens. Yeah, in fact, we will not have a good fit in this case, because I have some wrong things here, so some messed values here. So let me correct everything. So what I'm doing, I'm bringing to the same interval. I'm drawing everything from 0 to 3, say. So y lim, no need to correct x coordinates because x coordinates are okay here. Nothing mixed here, mess it here. So y lim is c, say I want to draw from 0 to say 3. Let's try with 3. No, this is not enough. Say let's do up to 3.5, say. Yeah, that's okay. Now I am copying this, and adding here. Running this to keep, oh, sorry. Running this to keep that. Now I have this, yeah. I have this shape. Okay, what I can do, let me do the following. Say I can add more beans to that. So I'm doing breaks. Breaks is equal to say 50. So I will have this kind of thing, and I'm running everything. Yeah. Again, I'm running that. Okay. Now I am increasing the number of points. If I will generate 100,000 points, then I will have this kind of fitting. So you can see that that theoretical PDF we have calculated 1/2 times square root of x is perfectly fitting that shape of the histogram. How many elements I will have in this interval, how many in this interval, how many in this interval. Well, in fact, not how many, but what proportion, because I am doing relative frequencies. The proportion of numbers in this interval or that interval can be calculated by that PDF. So this much about generating, checking that we have calculated that correctly, the PDF. Now, the next example is with exponential. So x is exponential with parameter lambda. Find the PDF of square root of x by step by doing all calculations and then by using the above PDF transform formula. So first let me do by hand calculating all steps for that. So x is exponential with parameter lambda, and y is the square root of x. So this is well defined because exponential random variable is taking only positive values, so I can calculate square root of x. Now, first I'm starting by calculating the CDF of y. So start from CDF of y. Then write the definition. I'm writing the definition. Now plugging the value of y. So probability that square root of x is less or equal than small x. Now do not remember that you need to solve this for any x, on any values of x. So if x is negative, I will not have any solution here. So I need to divide into two parts. If x is negative, I will have 0, that probability. If x is positive, I can solve, and the solution is this. If x is non-negative. Well, I forgot to write probability. Of course, the probability that this is less or equal than that. Okay, now I can express this in terms of CDF of x, random variable x. So 0 if x is less than 0. And this is exactly the CDF of x at the point x squared. Okay, well, now I can do in two ways, either to calculate the derivative, the plug, or first plug the value of this, then calculate the derivative. Let me do in this case in the second way. So I'm calculating the value of this first, then I'm calculating the derivative. So now I want to write the CDF of x at some point t. Because I have exponential distribution, this is standard and this is 1 minus e to the minus lambda times t if t is non-negative and 0 otherwise if t is positive. So I can calculate this. This is 0 if x is negative, and now I'm plugging instead of t that x squared. Because x squared is non-negative, I need to use this formula. So I will have 1 minus e to the minus lambda times x squared if x is non-negative. So now I have the CDF of y given in this way. I can calculate the PDF of that y. So let me just calculate. I'm just erasing this. Yeah. Now the PDF of y at the point x is the derivative of the CDF. And this is equal to the derivative of this. So two cases, 0, the derivative of 0 is 0. In this case, derivative of this will be, well, this will be 0, the derivative of 1 is 0, minus e to the that will be lambda times 2x times e to the minus lambda x squared if x is larger than 0. And I am not calculating at 0. This function will not be differentiable at that point. You need to check, maybe it is differentiable at that point. That is not important, in fact. So I can skip that calculation. Okay, so this is the PDF of our random variable y, calculated step by step. Now, let's go back. Okay. So by using the above PDF transform formula, solve the same problem by using that. So our g of x is square root of x. We are using this function. So y is equal to square root of x. This function is strictly increasing function. Square root of x has this form, so it is a strictly increasing function. So we can use that transform formula, and first I'm calculating the inverse. I'm solving in terms of x here to find the inverse. So x is y squared. So g minus 1 at y is y squared. And this works for y is non-negative. So y is non-negative. So this is that inverse function. In fact, let me write that inverse function in terms of x. I'm just plugging x instead of that minus 1. Sorry, I forgot to write 1. X is non-negative. So this is that inverse function. The inverse of square root of x is x squared, of course. Now I'm using that formula to make that transform. So no need for this. I just need the inverse. So that f of y at x, that formula was, for the case of strictly increasing function, was the following. Calculate the PDF of f at the point g minus 1 x and multiply by the derivative of this, g minus 1 x prime. So this is equal to, this is the PDF of exponential. So let me write that PDF of exponential, then I will plug that value. PDF of exponential at the point t is lambda times e to the minus lambda t if t is non-negative and 0 otherwise. Okay, so here I need to calculate fx at the point x squared. So g minus was x squared times x squared prime, so 2x of course, I'm calculating the value, plugging here x squared. So because I'm plugging non-negative value x squared here, I will have x squared. I will have only this formula. So yeah. So what I have is the following: lambda times e to the minus lambda times x squared. Yeah, I'm plugging x squared here. So x squared here, x squared here. And then that was the value of this. And then x squared derivative 2x. So this is, and this is working for the derivative of the inverse is defined for x is non-negative 0. So, and 0 otherwise. So x is negative, negative. So y, f of y is 0 when x is negative. Think about that. This is easy. Because, well, y cannot take negative values, so the probability density is 0 there. Okay. Now, the next problem is the following. We do not have that one of our famous distributions, so it is given in this form. In fact, this was one of the cases of beta distribution. So PDF is given by c times x to the 5, and f is 0 outside of this interval. So c times x to the 5 in this interval and 0 other outside. And y is x to the 4 plus 2. And the problem is asking to calculate to find the PDF of y. So first I'm calculating c. First step is to find that c. So I'm calculating that from the property of a PDF, any PDF. So the integral of PDF need to be 1 over the real line. And because f is 0 outside of this 0, 1, I will have only this integral over the interval 0, 1, c times x to the 5 dx. So this c goes out. I'm getting c times integral of x5 will be x to the 6 over 6 from 0 to 1. Plugged 1, then minus plug it the value at 0. So the value at 0 will be 0, the value at 1 will be 1 over 6, so I will have c over 6. c over 6 is 1, so c is 6. So here I have 6 instead of this c. Now we have calculated this. Let's solve the problem which is asking to find the PDF of y. So first I'm starting by CDF. The CDF of y is at the point x is by definition the probability that y is less or equal than x. And this is probability that x to the 4, I'm plugging the value of y, plus 2 is less or equal than x. Now I need to solve in terms of random variable x. So I'm solving that probability that x4 is less or equal than x minus 2. To solve this, I need to consider all cases. So this can be negative, and in that case, x to the 4 cannot be less or equal than that negative value. So considering two cases, if x minus 2 is negative, x is less than 2, that means, and if x is larger than 2, if this is positive, then the solution will be the following. Probability that x is between, including that point, fourth root of x minus 2 and minus that fourth order root of x minus 2. If x is larger or equal than 2. Now I can express this in terms of the CDF of x. So the probability that x is between a and b is CDF at this point minus the CDF at that point. So 0 if x is less than 2, and f x at the point fourth order root of x minus 2 minus fx at that point, fx at minus fourth order at x minus 2 if x is larger or equal than 2. Now we need to calculate this. Okay. Sorry. Now what I'm doing, I'm first differentiating this equality, this property, this the value obtained by this calculation. So I'm erasing this part. Now our aim was to calculate the PDF of y, not the CDF, so I need to calculate the derivative of that CDF. So PDF of y is equal to the derivative of CDF of y, and this is equal to the following. So I am calculating the derivative of this. 0 if, of course, if x is less than 2, and the derivative of this if x is larger than 2. So derivative of this will be first the derivative of capital F, which is giving the small f at the point fourth order root of x minus 2 times the derivative of this fourth power. So that will give this is x minus 2 to the power 1 over 4. So I will have 1 over 4 times x minus 2 to the power 1 over 4 minus 1. So minus 3 over 4. And minus, so I need to calculate also for this. So what will be the difference? The difference will be fx at minus that point, and times another minus sign here, so I will have plus sign here. So let me just erase this because I do not have space to write, and add that here. So what we have here, so fx at the point minus fourth order root of x minus 2 times 1 over 4, the same thing, and we have added that minus and we got plus here, x minus 2 to power minus 3 over 4 if x is larger than 2. Okay, now I need to calculate this. This is easy because I have that formula for the PDF of x. So because this is negative minus some positive thing, and f is 0 outside of this interval, then this total will be 0. So this is 0. So I am left with this. So I can just erase this. I'm erasing this part because this is 0, and I am calculating this value. So this is equal to 0 if x is less than 2, and 6 times the fifth power of this. So I'm plugging this into f. So fifth power of that times 1 over 4 times x minus 2 to the minus 3 over 4 over 3 over 4. If I am plugging here, I need to have, if I am using this formula, I need to have that this x is between 0 and 1. So if I am plugging this instead of that x, this needs to be between 0 and 1. So I'm writing fourth order root of x minus 2 is, well, this is always larger than 0, larger or equal than 0, so this is less or equal than 1. Less or equal than 1. And otherwise this will give 0. Otherwise this is 0. So 0 if fourth order root of x minus 2 is larger than 1. Okay, so it remains to simplify this. Just to simplify, let me erase this part maybe and simplify it here. So this is equal to, this is equal to the following. 0 I will write later in which case this is 0, because I will combine these two cases. Well, I can combine that. If I am solving this, this is x minus 2 is larger than 1, taking the fourth power of this and that. So x is larger than 3. If x is less than 2 or x is larger than 3. And if this is correct, this means that x is between 2 and 3. Otherwise, so if x is between 2 and 3, I will have 6 over 4, so 3 over 2 times x minus 2 to the x minus 2 to the 5 over 4 minus 3 over 4, so I will have 2 over 4, so square root of this, well, 1 over 2, if x is between 2 and 3. So this kind of formula for our PDF of this random variable. So this was, let me just add, this was fy at x. Okay. The next is the following. So I'm using my x continuous random variable as x, so this is continuous uniform from -1 to 2, but I'm making that kind of change of variables, that kind of transform that bring to discrete case, discrete random variables. So in this case, let's find the PMF of y. Y is discrete and we want to calculate the PMF of y. So find the distribution of g of x. G is given in this form. So let me solve the part A. So y is g of x, and this is equal to, I'm just plugging everywhere else, x instead of t. X is less than 1 and g of x is 1 if x is larger or equal than 1. So you can see that y is taking only two values, 0 and 1. So I'm writing y is taking two values, 0 and 1. So y is discrete. Okay, now what is the probability that x is, not x, y is taking the value 0? So probability that y is equal to 0 is the same as probability that x is less than 1. Okay, and this is easy to calculate because we are dealing with uniform probabilities. I'm thinking like this. I'm choosing x is some point between -2 and 2. I'm choosing uniformly point from -1 to 2. And what is the probability that x will be less than 1? So this is -1, 2. This is 1. I'm choosing a random point uniformly here. What is the probability that my point will be less than 1? So it is the probability is equal to the length of this over the total length. So I will have 2 over 3. The total length is 3. This length is 2. So the probability that y is 0 is 2 over 3, and the probability that y is equal to 1 is the probability that x is larger or equal than 1, and this is this part's probability. I'm choosing a point from -1 to 2. What is the probability that it will be larger than 1? And this is 1 over 3. Of course, we could obtain that from the condition that the sum of this is 1. So finally, I can state that I have obtained y to be Bernoulli, with parameter, well, I need to take the probability of 1 over 3. So this is the result. So starting from a continuous random variable, we made some transform and we have obtained a discrete Bernoulli random variable. Sorry. Now about this, so B, x can be, if x is uniform from -1 to 2, x is taking values from -1 to 2. So I'm breaking this into several cases. Well, if x is between -1 and 0, then the value of z, which is integer part of x plus 2, so in this case the integer part of x will be -1. So -1 here plus 2, so z will be 1. And the probability of that, z is 1, is the probability that x is between -1 and 0. And we have calculated that kind of probabilities. So this is -1, this is 0, 1, 2. We are asked to calculate the probability that x is between -1 and 0 if we are choosing randomly, uniformly points from -1 to 2. So the probability will be the length of this interval over the total length of this interval. So it will be 1 over 3. So probability is 1 over 3. Next is that x can be between 0 and 1. So in that case, the integer part of x will be 0 and the value of z will be 2. So z is 2. And the probability of that, so probability that z is 2 is the same as probability that x is here. And the probability that x will be in this interval is again 1 over 3. So the next case is when x is between 1 and 2. So z will be, integer part of x will be 1. 1 plus 2 is 3. So probability z is equal to 3 is equal to 1 over 3. Probability that z is equal to 3 is the same as probability that x is between 1 and 2. And the probability that x is between 1 and 2 is 1 over 3. And it remains to consider x is equal to 2. So in that case, z is equal to, integer part is 2. 2 plus 2 is 4. And the probability that z will be 4 is the same as probability that x will be 2. But because x is continuous random variable, this probability is 0. So we can just neglect this value of z. Z cannot be 4, take the value of 4. So we have obtained the following table, PMF. Z is taking value 1, 2, 3, with probabilities 1 over 3 all. 1 over 3, 1 over 3. So we have obtained it. In fact, z is discrete uniform. Let me write in this way, unif, with parameters 1, 2, 3, at the points 1, 1, 2, 3. Okay, this much about this example. So let's move forward. The next is again about discrete case. So x is continuous, but y is, the transform is discrete. So what we have, x is exponential with parameter 0.3. Find the distribution of y, which is 2 times integer part of x. So I'm writing the CDF. So I will use the CDF of x to calculate probabilities. The CDF at x, say, is 1 minus e to the minus lambda, that is minus 0.3 x if x is non-negative, and 0 if x is negative. Now, x can be, because x is exponential 0 with parameter 0.3, then x can take any positive values. Why is that? Because the shape of its PDF is like this. So 0 here and something like this. So x can take any positive values. So the probability that x will be here is this area much. The probability that x will be here, well, a small probability that x will be here, but it is positive. So positive probability that x will be here, etc. So x can take any real values. In fact, so let's break this into, because we are calculating integer part, break into subcases. So x is between 0 and 1, then y will be, the integer part of x will be 0, y will be 0, and the probability that y is 0, oh well, I'm not writing that correctly, the probability that y is 0 is the same as probability that x is between 0 and 1, and this probability is equal to, so I'm using CDF. So CDF of x at point 1 minus CDF of x at point 0. So because of continuity of a random variable, I can add equality sign, so I will have this. Okay, so easy to calculate. F at 0, so I'm using this formula for 0. At 0, I'm plugging 0, I'm getting 0 here. So this is 0. Fx at 1, I'm plugging 1, I'm getting 1 minus e to the minus 0.3. So I can start writing the distribution of y. So it is taking, it is discrete, so I'm writing the PMF. It is taking the value 0 with probability 1 minus e to the minus 0.3. Okay, so what will happen if x is between 1 and 2? Then in that case, the integer part of x will be 1, so the value of y will be 2, and the probability that y is 2 is the probability that x is between 1 and 2. And this is equal to, I'm again expressing in terms of CDF of x, f at 2 minus f of random variable x at 1. So this is equal to, well, I need to plug the values. We have calculated this is this much, and I need to calculate the value at the point 2. If I will plug 2, I will have 1 minus e to the minus 2 times 0.3. So if I will calculate this difference, I will have e to the minus 0.3 minus e to the minus 2 times 0.3. You can check that this is correct. So the next I'm adding to this table, y is taking the value 2 with probability e to the minus 0.3 minus e to the minus 2 times 0.3. Okay, so I'm erasing this part and continuing. So the next is to consider the case when x is from 2 to 3, etc. So, well, let me do the general case. So if x is between k and k plus 1, k is any non-negative integer value. K can be 0, k can be 1, k can be 0, 1, 2, 3, etc. Yeah. So in this case, the integer part of x will be k. So the value of y will be 2k. And the probability that y is equal to 2k is the same as the probability that x is between k and k plus 1. K plus 1. And I'm expressing this in terms of the CDF of x at k plus 1 minus the CDF of x at k, and this is giving again using that formula, e to the minus k times 0.3 minus e to the minus k plus 1 times 0.3. So I can maybe erase some part and add that value to the PMF and get the PMF of or y. So 0, 2, then 4, then 6. So this runs over non-negative even numbers. General form is the following. So y takes the value 2k with probability e to the minus k times 0.3 minus e to the minus k minus 1 times 0.3, etc. So, etc. So this is the final result, final answer. The distribution of y is like this. Okay, let's move forward. Another example, so important example, in fact. X is exponential. Find the distribution of 3 times x. So let me do that. First, I'm calculating the CDF of y. Probability that y is less or equal than x. And value of y is 3 times x. So probability that 3x is less or equal than x. So this is, I'm solving in terms of x. So I'm getting probability that x is less or equal than that small x over 3. Well, if I will express this in terms of the CDF of x, I will get that CDF at the point x over 3, exactly. Now, I can just plug the value of CDF of x. So CDF of x is the following. Because I have x is exponential, then I know the CDF. So the CDF is 1 minus e to the minus lambda t if t is non-negative, and 0 if t is negative. So I'm plugging that value. I'm plugging instead of t x over 3. So I'm getting the following. 1 minus e to the minus lambda times x over 3. If x over 3 is non-negative, well, this is the same that x is non-negative, so I can just erase and write x is non-negative, and 0 if x over 3 is negative, so this is x is negative. So we have obtained this value for the CDF of y, but we can see that this is the same as the CDF of the following random variable. If we will take exponential, but with parameter lambda over 3, this is exactly the CDF of that random variable. So our random variable y will be exponential with parameter lambda over 3. This is important. So I will give a comment about this. So in general, if x is exponential with parameter lambda and alpha is non-negative number, then alpha times x will be exponential with parameter lambda over a. So here we are multiplying. So 3 times x, the distribution is exponential lambda over 3. So if we are multiplying here, the parameter is divided by that number. So what is the interpretation of this? Say x is exponential. It is measuring the waiting time for some event in days, say. X is calculated in days. The unit of x is days. Then the average, this lambda is the average waiting times, then the average waiting times will be 1 over lambda. So recall the interpretation of this lambda. lambda was 1 over that average waiting time. So 1 over lambda will be the average waiting time in days, of course. Now, say, why is the waiting time in hours? Say, if I'm waiting in average 2 days, then I will have 48 hours. So I need to multiply by 24. So assume y is, I was not correctly saying, let's talk about not the average, but exact waiting time. So exact waiting time in days is x. Say I can wait 2.3 days for something, for the next event. So I want to calculate that in hours. So to obtain that value in hours, I need to multiply by 24. So let y be the waiting time in hours for the next event. So y is 24 times x. Now, the average waiting time in hours will be, so average waiting time was 1 over lambda days. So if I want to calculate that in hours, that will be 24 over lambda hours. So if average waiting time is this much in hours, then my waiting time will be exponential with parameter 1 over this, 1 over that average value. So y will be exponential with inverse of this, that parameter. So I've obtained that 24 times x is distributed as exponential with lambda over 24. So we are dividing. X was with parameter lambda, 24x is with parameter lambda over 24. So this is important when doing change of unit of calculation, say. Question, if x is exponential with parameter lambda, what can be said about x minus 3? So if I'm multiplying by something, that is again exponential. Will this difference be exponential? In fact, no, because x is exponential, x is taking values from 0 to infinity, and more chances that x will be around 0 because the PDF was of this form. Close 0, we have more mass, more area. X minus 3 will take negative values close to minus 3. So this cannot be exponential anymore. Okay, another important example. Assume x is normal with parameters 0, 1, standard normal. So x is standard normal. Find the distribution of e to the x. So I'm starting by the CDF of y. This is probability. Well, y is less or equal than x. I'm writing e to the x is less or equal than small x. Now, to solve this, I'm remembering that x can be anything. So if x is negative, I cannot solve this. So 0 if x is negative. Even if x is 0, e to the some power cannot be less or equal than 0. So in this case, this is 0, probability is 0. And if x is positive, I'm just logarithming, taking the logarithm. X is less or equal than logarithm of small x if x is positive. Well, I can express this in terms of the CDF of x. So this is equal to 0 if x is less or equal than 0. And this is the CDF of x at the point logarithm of x. Okay, I do not have in a good format as a good expression, good format expression, the CDF of normal 0, 1. This is integral, some kind of integral. So let me calculate the PDF of y. So let me calculate first the derivative of the of two sides of this equality. So fy, the PDF of y at point x, is the derivative of this. So fy CDF derivative. And this is equal to, I'm calculating the derivatives here, 0 if x is less than 0. And the derivative of this will be the derivative of this function, which is giving the PDF of x at logarithm x at that point, times the derivative of this function, which is 1 over x, if x is positive. Now I need to plug the value of this. So let me erase this part. This is not necessary anymore. So I'm continuing by plugging that value. So 0 value of PDF of x, PDF of standard normal. 0 if x is less than 0, and the following is the formula. 1 over square root of 2 pi. So sigma times square root of 2 pi. Sigma is 1 and mu is 0. Times e to the minus, here I need to have x squared over 2, but instead of x I'm plugging logarithm of x. So logarithm x squared over 2, and times this derivative of logarithm, which is 1 over x, if x is positive. So this is the PDF of y e to the x. So why is this important? Because the distribution of this y is called the log normal. It is important, say, in financial math, to describe, to give the distribution of prices of different stocks. If we will have mu sigma squared, then y is log normal with parameters mu sigma squared, because we were doing only for 0, 1. The distribution of y is called the log normal with parameter 0, 1. The name log normal is because the logarithm of this, the logarithm y, will be x, which is normal. The logarithm is normal. Okay, the next, we are close to the end of this lecture. So x is uniform in 0, 20. Find the shape of the distribution of this. Well, I cannot do this example by hand because I cannot solve this is less or equal than x in terms of x, but find the shape of the distribution of this random variable in R. So let me do that. X squared over 1 plus x plus logarithm x, and 0 to 20. Okay. So what I'm doing, I'm first erasing this. X was uniform, so I'm generating uniform numbers. R unif. Yeah. From how many points I want to have, say 1000, then I will increase that number from 0 to 20. From 0 to 20. Yeah. I have my x. Now I'm calculating that y. Y was x squared over 1 plus x. 1 plus x. Sorry. Yeah. And plus logarithm of x. Logarithm of x. And base is e. Yeah. So I have y. Now I can do the following histogram of x, not x, sorry, y, transform numbers. Breaks, let me take breaks to be, say, 50. Auto breaks. And let me take frequency, because I want to have shape of PDF. Let me take frequency is equal to false. So this is the shape of that histogram. So, well, to get a better result, let me increase this to 100,000. So I'm running this, and running that. So this kind of shape. So many values are between, say, 0 or maybe 3 to 20 something, small number of values between say -10 and 0. You can see. Okay, there is another thing, thing we can do with this. This is called kernel density estimator. In R, this is density. Just we are writing. Sorry, we are writing density. Density of y. Density of y. To obtain some approximation for the PDF, and now I can just do plot f. This is the shape of some approximation. The real shape I do not know and computer doesn't know, but this is the approximate shape of the PDF of that random variable. So this is called kernel density estimator, KDE. Okay, this much about this example. So some facts about linear transforms of random variables. So if x is uniform in some interval ab and alpha is positive number, then alpha times x plus b, if we are doing linear transform to x, then that will be again uniform, and the parameters will be alpha times a plus beta and alpha times b plus beta. You can easily consider the case when alpha is negative. Just we need to switch these places. Say one example, if say x is uniform from 2 to 5, then say minus 2x plus 4. What is the distribution of this? I'm starting from minus 2 times x. This will be uniform. I'm multiplying this by minus 2 minus 4 minus 10. So I'm starting from minus 10 to minus 4. And I'm adding 4 minus 2x plus 4 is distributed as uniform. Minus 10 plus 4 minus 6 and minus 4 plus 4, which is 0. So the distribution of this random variable will be uniform from minus 6 to 0. Okay, this is about uniform. If we have if our x is exponential with parameter lambda and alpha is positive, then we have talked about this, that alpha times x is exponential with parameter lambda over alpha. And if I will add or subtract something, that will not be any more exponential. So when doing transforms, we can obtain random variables that are not of the same family of distributions. And nice thing is that we can do linear transforms with normal distribution and obtain another normal distribution. So if we are calculating alpha x plus beta, this random variable will be again normal with parameters. Well, mean is we are just plugging mean here, alpha mu plus beta. And for variance, beta is not important because if we will shift from here to there, shift is not changing the variance. Shift is not changing variance, so we are getting in the variance alpha squared times sigma squared. Later we will talk about this when we will define what is the mean and variance of general random variable, not only for normal ones. Okay, another important, very important in terms of computations, computational mathematics or generating random numbers. Assume x is continuous random variable with a strictly increasing CDF f of x. So I have CDF of this form. So this kind of CDF, well, it tends to 1. This is my f, strictly increasing CDF. And we are defining y to be f of x. So what I am doing in the CDF of x, so f of x was its CDF. I'm plugging that x itself. So I'm not plugging my x into any function g, but I'm taking its PDF and plugging that random variable into its PDF. So this is our new variable y, random variable y. So show that y is uniform in 0, 1. Very nice result. If you will plug the random variable into its CDF, then you will get uniform 0, 1 every time. If, well, this is strictly increasing. Proof is simple. So I want to calculate the CDF of y. So this is the probability that y is less or equal than x. And this is the probability that f of x is less or equal than x. Okay. Nothing new here. Now I need to solve this, but because f is strictly increasing, so I can solve that by x is less or equal than f minus 1, the inverse at the point x. Well, we have done this kind of things with j. J was strictly increasing. This is f is strictly increasing, so we can solve this. Okay, what next? So the next is the following. I can express in terms of the CDF of x. So this is the CDF of x at the point f minus 1x. But recall that the CDF of x was f, the same f. So I'm writing f at the f minus 1x. Well, and this is x. Well, this works if x is between 0, 1. Let me explain why it works when x is 0, 1. Okay. If x is, let us consider the case when x is negative. If x is negative, then I need to calculate this probability that f of x is less or equal than negative number, but the values of CDF cannot be negative. So if x is negative, I need to obtain 0 here. So I will obtain 0 here. If x is larger than 1, if I will write what is the probability that f of x will be less or equal than 1, well, all values of CDFs are less or equal than 1. So if x is larger than 1, then we are getting 1 here for the probability. So all cases are satisfying. So at the end, we will have the following. So this is equal to x if x is between 0 and 1. If x is negative, we will get 0. So no value is satisfying, so probability is 0. If x is larger than 1, all values are satisfying this inequality, so we are getting 1. So let me just summarize. Summarizing, I will have the following. F of y is the following. So it is 0 if x is less than 0. It is x if x is between 0 and 1. And it is 1 if x is larger than 1. So we are getting this kind of graph for that CDF of y. This is 1, this is 1. So that means that y is exactly uniform with parameters 0 and 1. Okay, the first part is solved. So the second part, maybe this is more important. Y is uniform, and we have a continuous strictly increasing function with f at minus infinity is 0 and f at plus infinity is 1. So f is a CDF of some random variable. Now we are defining x to be f minus 1 because it is strictly increasing. We will have the inverse function well defined. And I'm calculating the inverse function at y. This is my new random variable. So show that the CDF of that random variable x is f. So y is uniform, f is any function. We are calculating f minus 1 at y. So this new random variable will have the CDF f. Again, easy to show. So let me calculate in this case, our new random variable is f of x. So I'm calculating the CDF of random variable capital X. So this is the probability that x is less or equal than x. So this is the probability that f minus 1 at y, so I'm plugging the value of x, which is f minus 1 y, is less or equal than x. Again, because f is strictly increasing, the inverse is strictly increasing too. So, sorry, this is, yeah, this is equal. So, so f minus 1 is strictly increasing too. So the solution of that will be probability that y is less or equal than f of x. Now, this is equal to f of y at the point f of x. F of y, the CDF of y at this point. Okay, but recall that y is uniform. If y is uniform, I have the formula for fy. F of y will be something like this. So it is 0, linear, and 1 after 1. So this is 1, this is f of y in our case. Okay, so f of y will be x. This is the graph of x if our point is between 0 and 1. But f of x is between 0 and 1. The values of f of x are between 0 and 1. So fy at this point will be exactly f of x. Because this is between 0 and 1, then f of y at that point will be exactly the same value, f of x. So we have obtained that the CDF of x is exactly equal to f of x. Let's move forward. Informally, we can do the following. So y is f of x. So I'm solving x is f minus 1 of y. Y is uniform, and x is x has the CDF f. I'm writing in this way. So x, some tilde f. I mean that x has this CDF. Now, if x is normal, standard normal, and capital phi of x is its CDF, what is the distribution of phi of capital X? So I'm plugging random variable into its CDF. So we know that this is uniform 0, 1. Uniform 0, 1. No need to do any calculations. Well, this is strictly increasing continuous function, so everything is working okay here. Now, the next thing, recall that we were at the beginning of our talk about random variables, we were considering which functions can be CDF of some random variables. So, and we were considering sigmoid function. Sigmoid function is this, given by this formula, and we have studied, we have checked that this satisfies all properties of CDF. So this is a nice CDF. There is a random variable behind that. Now, the problem is the following. Okay, if this is a legitimate CDF, find a random variable for which this will be CDF, it's CDF. So find a random variable behind this CDF. Well, I'm using the previous example, previous problem. So that was saying that if y is uniform, and if I will calculate f minus 1 at that uniform, then the distribution of this new random variable will be exactly given by CDF f. So what I need to do, I need to calculate the inverse of this function, plug this y, and that obtained random variable will have this CDF exactly. So I'm doing that steps. So first I'm calculating the inverse function of this sigma, inverse of sigma. So let me write y is equal to 1 over 1 plus e to the minus x. To find the inverse of this, I need to solve this in terms of x. So 1 over y is equal to 1 plus e to the minus x. So e to the minus x is equal to e to the minus x is this minus 1. So 1 minus y over y. So minus x is equal to logarithm of 1 minus y over y. And x is equal to logarithm y over 1 minus y. Yeah. So the inverse function, let me write here, sigma minus 1 at the point y, or let me write with x. At the point x is logarithm x over 1 minus x. I'm just writing x instead of y, not to write sigma minus 1 at y is equal to y 1 minus y. And the name of variable is, again, I'm putting x. Okay, so I have this. Now everything is ready to obtain that random variable. So I'm taking y, which is uniform in 0, 1, and I'm calculating the inverse of this CDF at the point y. So this random variable, logarithm y, capital Y over 1 minus y, will have that distribution given by CDF sigma. So this is that random variable, logarithm y over 1 minus y. This random variable will have sigmoid CDF. To check the last result, to check that this is correct, generate random numbers in R and obtain empirical CDF. So I want to show that this is correct. This is working okay by using R. So let me erase, go to R. So I'm erasing this. Now what I'm doing, I'm generating Y uniform, R unif. So how many points? Say 1000. First, let's start from 1000. So I'm calculating that transform. X was logarithm y over 1 minus y. 1 minus y. I'm calculating this. Now I need to compare the CDF of this, not the PDF, so histogram will not work. But in R we have the following function. This is called empirical CDF. So let me denote by F. Sorry. Yeah. So ECDF, empirical CDF. CDF obtained CDF obtained from data, from empirical data of X, that calculated values. Now I am doing plot F. Maybe I will add line with this 2. So this is empirical CDF. Now let me add to this the graph of sigmoid. So the graph of sigmoid was, well, if I want to draw a graph, I'm taking a sequence of values, yeah, from say -6 to 6, -6 to 6, with size steps 0.01. Okay. Now I'm calculating the value of sigmoid at that point. So this is again easy. 1 over 1 plus exponential of minus t. So this is that. And I am adding, well, keeping the last graph plot, and then plot TZ, type is line, and the line width is, say, line width is 2, and color, let me do in other color, color is red, say, red. So I'm okay. So you can see, well, if this will open, then we will see, otherwise we will not see. Not a perfect match here, you can see, okay. But something is wrong with numbers, -4, -5. So again, I need to adjust. In this case, y values are adjusted, but x values are not adjusted. So let me do the following. Plot this with xlim from -6 to 6, -6 to 6, and copy this, everything. I'm copying and adding it here, and I will run everything. Well, no need for this. Selecting everything and running this. So you can see almost perfect match. If I will increase this, say 10,000 points, and run that, you will see a perfect match. So empirical CDF in black is almost coinciding with the sigmoid function itself, the theoretical CDF. Okay. Now, what next? The result is very important because of the use in generation of random numbers. So there is a method called transformation method, inverse transformation method. That inverse transformation method is as follows. So assume we want to generate random numbers from a distribution given by strictly increasing CDF f of x, like we have done for that sigmoid function. We do the following. We calculate the inverse function f minus 1 and generate standard uniform random numbers, that y, and then we are plugging that values at f minus 1. So we are calculating f minus 1 at that numbers, and this new data set is giving random numbers from that CDF, from our distribution with CDF f of x. One drawback here, you need to calculate, first you need to have that f is strictly increasing function, which is not always the case. And the other thing is that you need to be able to calculate f minus 1 for any x. So this is again not so easy if that f is some complicated thing. Even in some cases you do not have that f in the explicit form. You have the PDF, you need to integrate, say, for a normal distribution, f of x is not given in terms of elementary functions, so calculation of f minus 1 is almost impossible. Another note that for that example about f of minus 1 y or f of x, that method will work also in the case when f is of this form, so one of these forms. So let me just explain what I am writing here. Yeah, f can be of this form, say 0 up to some point, then strictly increasing, then 1 after some point. Then that example will work well in this case too. Or if f is of this form, so it is 0 up to some points, some point, it is 0 up to some point, then it is increasing and tending to 1, increasing tending to 1. So not 1 from some point on, but it is increasing and tending to 1. Say exponential is of this form. So it is 0, the CDF of exponential is 0 up to 0.0, then it is increasing and tending to 1 at plus infinity. Or we have strictly increasing from minus infinity, then 1 after some point. So this is important, but for this case, say, if I will have CDF of this form, say 0, then increasing, then constant, then increasing, then constant, 1, say, well, this method will not work with f minus 1. F minus 1 will not be defined at some point, but there is a method to overcome that by using quantile functions, in fact. But let's skip that. Okay, the next example is the following, using only standard uniform random numbers. So we can use only standard uniform 0, 1 random numbers. If you remember when I was talking about when I was talking about uniform distribution, I was stating that standard uniform is very important because generation of other random numbers, other distribution random numbers usually are based on generation of standard uniform random numbers. Now I want to give an example. Say, by the way, we have considered how to generate discrete random numbers. Now I am generating exponential 2 random numbers. So generate random numbers from exponential 2 distribution in R. And plot histogram and plot the PDF to compare them. So what I need to do, So I am first writing the CDF of that. Say x is my exponential, x is exponential with 2. So CDF will have the following form. 1 minus e to the minus 2x if x is non-negative, and 0 otherwise x is negative. As I mentioned already, this is of this form. So it is 0 up to some point, then increasing and tending to 1 after that. So we can apply that method of generating random numbers from F. So what was that method? That was saying take uniform, standard uniform, y, then plug into f minus 1. If you will plug that y into f minus 1, you will obtain random variable with this CDF. So random numbers of this form can be obtained from this distribution can be obtained by generating random numbers from y, then plugging into f minus 1. Now I need to calculate f minus 1. The probability that my y, generated y, will be 0 exactly is 0. So I can just calculate the inverse of this part. Well, f is not invertible at this point, but that's okay. It is enough to invert this, calculate the inverse for values in this range. Well, the inverse function will be defined from 0 to 1, not including 0. Okay, so inverse function. So what I'm writing y is equal to 1 minus, inverting this part only, 1 minus e to the minus 2x, solving for x, so e to the minus 2x is equal to 1 minus y, so minus 2x is logarithm of 1 minus y, and x is minus 1 over 2 logarithm 1 minus y. So the transform will be the following. So take y, that is uniform. This is small y, and here I have random variable uniform from 0 to 1. and calculate minus 1 over 2 logarithm 1 minus y. Then the distribution of this will be exponential with parameter 2, in fact. Let us check by doing generation of random numbers simulations in R. By the way, if y is uniform in 0, 1, then 1 minus y will be again uniform in 0, y. So we can just take y here instead of 1 minus y, but I will do this. Okay. So what I'm doing, I'm changing this. So I'm generating, say, y, which is uniform. So 10,000 random numbers from uniform 0, 1. I'm calculating I'm calculating the following: minus 0.5 times logarithm of 1 minus y. Erasing this part and erasing that part. Running this. Now let me plot the histogram. So in this case I'm doing histogram because I want to compare with PDF. So histogram is hist of x. Let me add breaks. Breaks is equal to 50. Do this. X lim is equal to, say, 0 to say 7, and y lim is, let me take y lim is equal to, say, from 0 to, say, 3. Let me check if this is working okay. No, not everything is visible. So let me add 0 to, say, 8. Again, not enough. Well, yeah, I forgot to add, I'm thinking why it's not working, because I need to calculate not the frequencies, how many elements are here, but relative frequencies, the proportion of elements. So I need to add frequency is false. Yeah, and now I can change back to, say, 2. You can see that exponential shape already. And let me change this 7. This is large enough to 5, say. Okay, even we can take 3, but that's okay. Now I want to add to this the PDF of exponential 2. So to have that PDF of exponential 2, I'm taking a sequence. I need to draw that PDF from 0 to say 5. Yeah. Here I'm writing the PDF of exponential 2. I can do in 2 ways, explicitly, or just write d exponential. This is the PDF, d exponential, calculated at the point t and with parameter 2. Yeah. So I'm keeping this and I'm adding this, but I need to change that plot range. So I'm changing that plot range. Okay. So let me run everything from the beginning. So selecting and hitting Control and Enter. And zooming to obtain. Yeah. So let me just change this to 100,000 and run that again. This is what we'll have. So you can see that we have nice, very nice match, perfect fit for that. Okay, this much. So this was all I wanted to give for transformation of random variables. So thank you, bye.